The universe is expanding, faster, farther, everywhere at once, and yet there is no outside for it to spill into. Imagine reaching the edge of everything, only to discover there is no edge to stand on. So when cosmologists say space is stretching, what is it expanding into, and what does nothing even mean? Look closely at the night sky and you are not seeing space, you are seeing time, layered like glass. The farther we look, the stranger the stage becomes, and the rules we trusted begin to fail. In everyday life, distance feels fixed, like a ruler laid across a table. Yet the universe does not treat distance as a permanent fact. On cosmic scales, it behaves like a living quantity. The expansion we measure is written into geometry itself. It is not a story of matter rushing through a surrounding emptiness, but of the metric that defines far quietly changing. To make sense of that claim, we must learn what modern physics means by space and what it refuses to mean. We will watch light act as a time capsule, its stretched wavelengths carrying a record of how the cosmos has grown. We will meet the observations that forced this picture into existence, from early spectral shifts to the sky's faint microwave afterglow. We will see why every direction can look like recession without granting any location the dignity of being central. Then the questions sharpen. Empty space, quantum vacuum, and the absence of space-time itself are not interchangeable, and the universe exploits that difference. Along the way, we will confront a Big Bang with no preferred center and an early growth spurt that reshaped what could ever be observed. We will trace horizons that limit what information can reach us, even in principle, and why those limits matter. And we will return to the original paradox with new tools in hand: scale factors, curvature, topology, and a careful distinction between coordinates and reality. Some answers will feel almost simple once stated, while others will deepen the mystery in a more disciplined way. Because the real tension is not a lack of imagery, but a clash between intuition and mathematics. When physics sets the rules, outside may be the wrong category entirely, and nothing may be far from empty. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by dismantling the container picture, then rebuild it using relativity, evidence, and the universe's oldest light. By the end, the question will remain. Yet, it will be the right question, asked in the right language. Galaxies drift apart in every direction, and the gaps between them quietly widen as if the cosmos is exhaling. On screen, pinpricks of light slide away from one another, and the darkness between them grows more pronounced with each passing beat. The first question sounds childish, but it refuses to go away in the mind. If everything is expanding, where does the new space come from? If there is no outside, what could expansion even mean? Our everyday intuition is blunt and practical, built from rooms, roads, and the edges of things we can touch. To expand, something needs room around it, and it needs a boundary that can push outward. A balloon swells because air pressure pushes the rubber outward into the surrounding room, and the room is already there. A crowd spreads because there is open ground beyond its edges, and the edge is visible. Expansion, in daily life, is motion into pre-existing space, and we rarely question that hidden assumption. That intuition is useful, and it is also the trap, because it smuggles in a container without asking permission. The universe is not an object sitting inside a larger box waiting for extra volume to be granted. When cosmologists say the universe expands, they do not mean galaxies fly through space into emptiness beyond a boundary. They mean the distance between faraway galaxies grows because space itself changes, and the rule for measuring separation evolves. This is the core confusion we have to hold on to, even when it feels slippery and abstract. We picture an expanding thing with an edge, a center, and an outside, because that is how objects behave in our experience. Modern cosmology describes an expanding geometry with no required edge, no preferred center, and no meaningful outside. The phrase expanding into nothing smuggles in the wrong picture, and then asks us to solve a paradox it created. So we start with what we can actually measure. We cannot step outside the universe to watch it from a distance, and we cannot rewind cosmic history like film. We infer expansion from light that reaches us across billions of years, arriving as a kind of time capsule. We read the universe through spectra, through patterns, through a consistent drift in wavelength that repeats across the sky. In the visuals, the camera rides a photon's path, passing silent voids and faint halos of galaxies. In the 1920s, astronomers found a striking regularity in the data, and it did not arrive as one clean revelation. Vesto Slipher had already measured large redshifts in spiral nebulae, and Henrietta Leavitt's Cepheid variables helped build the distance ladder. Then Edwin Hubble used those tools to show that many nebulae were galaxies far beyond the Milky Way, and the patterns snapped into focus. The farther a galaxy is, the more its light is shifted toward the red. Edwin Hubble and Georges Lemaitre connected that trend to a simple relation that could be tested. Recession speed is roughly proportional to distance, and v is approximately h0 times d. That equation is not a single dramatic event, and it is not a claim about one privileged direction. It is a pattern seen in many directions for many galaxies, across large scales and different surveys. It does not point to one spot in the sky where everything is fleeing from an explosion. It points to a universe where separation increases everywhere at once, as if the grid of space is being gently stretched. Redshift is the observational clue, but it is also a source of misunderstanding, because it sounds like ordinary motion. Red light has a longer wavelength than blue light, and that wavelength is a measurable physical spacing between wave crests. When a spectral line moves toward the red, the wavelength we detect is longer than the wavelength emitted. Something happened during the light's journey, and the spectrum preserves a record of that change like a barcode. One familiar cause is Doppler shift, and we know it from sound long before we meet it in astronomy. A siren sounds lower as it moves away because the waves are stretched by motion through air, and the spacing between crests increases. Light can also be Doppler shifted when a galaxy moves through space relative to us, and nearby galaxies show this kind of motion. Those local velocities matter for clusters, for collisions, and for the gravitational dance of neighbours. In close-up visuals, galaxies swirl around one another, and their motions look like ordinary trajectories. Cosmological redshift is different in a crucial way, and the difference is not merely semantic. On very large scales, the dominant effect is not galaxies speeding through static space, like debris in a blast. The effect is that the space between emission and detection has expanded, and the light travelling through it is stretched too. The photon's wavelength lengthens because the metric it rides upon changes while it is in flight. A useful shorthand is that the wavelength grows with the scale of the universe, and the relationship is direct. If the scale factor doubles during the light's travel, the wavelength doubles as well, and the observed colour slides toward red. The photon does not need to lose energy to a surrounding medium because there is no cosmic fog doing the work. The geometry it moves through changes, and the wavelength records that change with ruthless honesty. This is where language starts to fail us, because our verbs were built for objects moving in rooms. We say galaxies are receding, and we picture them as rockets leaving a launch pad. But in metric expansion, the recession is built into the distance measure itself, not into a shared wind of motion. Two galaxies can be nearly at rest in their local space, each feeling no rush of speed in its own neighbourhood, yet their separation still increases over time because the space between their neighbourhoods is being stretched. That claim sounds like a trick, so we anchor it to what is observed and what is checked repeatedly. The redshift distance relation holds statistically across the sky, even when we average over the messy details of local motion. It is not limited to one hemisphere, and it does not weaken when we look away from any supposed centre. The expansion appears uniform in every direction we can see, and that uniformity is itself a clue. Uniform in every direction is a loaded phrase, and it leads to a principle that quietly organises the entire field. The cosmological principle says that on sufficiently large scales, the universe is homogeneous and isotropic, at least in a statistical sense. Homogeneous means no special location stands out when we zoom out far enough, and isotropic means no special direction stands out. The universe looks broadly the same from any typical vantage point, even though it is wildly structured up close. This principle is not a philosophical preference, and it is not a declaration that everything is literally smooth. It is a compact summary of what large surveys and the cosmic microwave background suggest, and it survives repeated attempts to break it. The universe is clumpy on small scales, with stars and galaxies and voids, and those details are dramatic, but averaged over hundreds of millions of light years, the distribution smooths out, and the statistics become strangely simple. If the universe has no preferred center, our usual explosion story collapses in a very specific way. In an ordinary blast, debris flies away from a single point in pre-existing space, and you can draw arrows back to the origin. In the cosmic expansion, every observer sees distant galaxies receding, and those arrows do not converge on a single location. Every galaxy can treat itself as the center of its own observable sphere because the pattern is built into the geometry. That creates the first major tension beat, and it is the one that keeps returning in different disguises. If there is no center, where did the Big Bang happen, and what does the word happened even refer to? If everything was once closer together, what was it closer together inside, and what counted as inside? If the universe was smaller, what was outside it while it grew, and why should there be an outside at all? These questions feel unavoidable because our brains demand a container, and our language keeps offering one. For now, we do not resolve them, because the wrong answer is easy and it is visually seductive. The wrong answer is to imagine a fireball expanding into empty darkness beyond an edge, like shrapnel spreading through a void. That picture makes the phrase expanding into nothing sound like a paradox, and then it dares us to fix it. It makes nothing into a place, and it makes the universe into an object with a boundary. The better approach begins by separating two ideas that sound similar, and then noticing which one physics actually uses. There is space as a stage, where events happen against an unchanging backdrop, and there is space as part of the play, where the backdrop can bend, stretch, and evolve along with the actors. In general relativity, space-time is not a passive background, and that is the conceptual pivot. It is a dynamical entity with geometry that can evolve, and distances can change because the metric changes. Metric is a technical word, but the intuition can be kept simple without losing its bite. A metric tells you how to measure distances and times, and it encodes what counts as straight and what counts as far. If the metric evolves, the meaning of a fixed coordinate separation evolves, even if the coordinates look unchanged. Expansion is not about matter moving into an external volume, and it is not about a frontier pushing outward. Expansion is about the rule for measuring separation changing with time, everywhere at once. Even that statement raises a deeper worry, because it sounds like we are redefining reality rather than describing it. If the metric changes, what is it changing relative to, and how do we know it is not just a coordinate trick? If space expands, does it expand into something else, like a fabric stretching into a higher room? The temptation is to demand an embedding space, a higher dimensional container where our universe sits and grows. But the mathematics of cosmology does not require that picture, and the observations do not point to it. A universe can be finite without an edge, like the surface of a sphere is finite without a boundary, and that example is more than a cute analogy. On that surface you can travel forever and never find a cliff, and the geometry never instructs you to stop. There is no special point that counts as the center of the surface, and no compass direction that leads outward. The center exists in a higher dimension, but the surface does not need access to it, and its inhabitants do not measure it. That analogy is limited, but it is useful for one reason, and we should name that reason clearly. It shows how asking what is outside can be the wrong question, because outside may not be part of the geometry being described. For a two-dimensional creature living on the surface, outside is not a location it can reach or even define operationally. The geometry is complete without an external reference, and the creature's physics can be self-contained. Cosmology applies a similar lesson in 3 dimensions, although the real universe may be more complicated than any single picture. The universe might be infinite, extending without bound, with no global edge to speak of. Or it might be finite, with a topology that has no edge, looping back on itself in ways that are hard to visualize. In either case, expansion does not require a surrounding emptiness, and it does not demand a cosmic wall. It requires a time-dependent scale in the geometry, a changing relationship between co-moving points. Still, the word nothing keeps returning, and it carries baggage that physics has spent a century unpacking. In everyday speech, nothing means an empty region, a blank container with no stuff, no air, no dust. In physics, nothing can mean several different things, and each meaning has consequences. It can mean vacuum, which still has fields and fluctuations, and it still permits virtual activity in quantum theory. It can mean the absence of space itself, which is harder to define, because definition usually assumes a stage. So the central question sharpens, and it becomes less childish and more precise with each pass. When we say the universe expands, what exactly is expanding, and what quantity is changing in our equations? When we say there is no outside, what exactly is missing, and what would count as outside in measurable terms? When we say nothing, do we mean empty space, quantum vacuum, or the absence of any space-time at all? Each meaning changes the paradox, and each one points to a different kind of answer. At this stage, the evidence gives us a direction but not a complete picture, and that is an honest place to pause. Redshift tells us the scale of the universe has changed during the light's travel, and it does so with a measurable factor we can compute. The Hubble, Lemaitre law summarizes the present-day trend, and the constant h0 becomes a number we argue over with increasingly precise instruments. Homogeneity and isotropy tell us the trend is not centered on us, and not aligned to a cosmic axis. These are constraints that any explanation must respect, and they narrow the space of possible stories. But constraints are not yet understanding, and a pattern is not yet a mechanism. We still need to connect observation to a model of space-time, and then test how well that model predicts what we see. We need to see how general relativity turns expansion into a property of geometry, rather than a spray of matter. We need to ask what the Big Bang was if it was not an explosion at a point, and what it means to say everything was once hotter and denser. We need to confront horizons because we only observe a finite region, and the limits of observation shape our questions. This is the roadmap for what comes next. We will build the idea of cosmic geometry and the scale factor, and we will treat it as a measurable feature, not a metaphor. We will use general relativity to explain why expansion is not motion through space, even when the language tempts us to say it is. We will examine inflation and why early expansion complicates the story, especially when we try to picture beginnings. We will define horizons and why the observable universe is not the whole universe, even in principle. And we will return to the word nothing, because it hides multiple concepts behind one casual syllable. We will ask whether the universe needs an outside at all, or whether that demand is a leftover from everyday thinking. We will ask whether the question expands into what is meaningful or misguided, and how physics decides the difference. We will keep the mystery intact, but we will replace the misleading picture with a sharper one that fits the data and respects the geometry. For now, hold on to the paradox in its cleanest form, and let it stay slightly uncomfortable. The universe expands, and the evidence is written in stretched light, arriving from deep time with its wavelengths elongated. The expansion looks the same in every direction, with no special center implied and no edge revealed. Yet our intuition insists expansion needs room, and it keeps asking what lies beyond the last galaxy. In the next chapter, we start dismantling that intuition with geometry, and we learn to see space as something that can change. The question from Chapter 1 keeps its grip because it feels practical, almost like a carpentry problem. If distances grow, what are they growing into? And where would that into even be? Hold that question in your hands as an image, because the mind solves pictures before it solves equations. Picture a dark stage with tape marks on the floor, and then imagine the tape marks sliding apart under a single spotlight. Your intuition immediately demands a larger floor beneath them, some hidden warehouse of emptiness waiting to be revealed. That demand is not foolish. It is the default model we inherit from daily life, where rooms have walls and floors have edges. The pivot is not an exotic answer about hidden rooms beyond reality. The pivot is a different question. What is space in our best theory, and what does it mean to measure distance? Because distance is not a pure idea. It is an operation carried out by physical systems with limitations. It is what happens when you compare ticks of a clock, marks on a ruler, or pulses of light bouncing between mirrors. Even the cleanest measurement is a choreography of matter and radiation, atoms vibrating, photons reflecting, electronics counting. In physics, the deepest questions often begin when we ask what an everyday word really refers to. In everyday thinking, space is a container that stays put while things move inside it. In that picture, expansion must be motion of matter into pre-existing emptiness. The container sits there like a box, and the contents rearrange themselves within the box, as if the box were immune to what happens inside. That intuition is strengthened by almost every visual we grow up with. and it is reinforced by language itself. Smoke spreads through a room, ink diffuses in water, crowds pour into a stadium, and a balloon fills a larger volume. In each case, there is an already there volume waiting to be filled, and the boundary is easy to point to. General relativity breaks that picture at the foundation, and it does so with a precise replacement. Space and time are not a passive stage. They're a dynamical geometry that can change. To see why this is such a radical shift, imagine removing the stage entirely and keeping only relationships. The distances between actors are no longer measured against a fixed floor. The floor itself can stretch, tilt, or ripple under their feet. The background becomes part of the cast and it responds to what happens on it, quietly, continuously, and according to law. Gravity, in this theory, is not a force pulling across a fixed background. Gravity is curvature. Geometry shapes motion, and matter shapes geometry. That sentence can sound like a metaphor until you connect it to what we can test with instruments. Light bends near the sun because the shortest paths in curved space-time are not straight Euclidean lines, even though the light locally goes straight. Clocks tick at different rates in different gravitational potentials because time itself is part of the geometry, and 1 second is not universal in the way Newton imagined. The slogan is compact because it is accurate. Space-time tells matter how to move, matter tells space-time how to curve. That slogan is not poetry, and it is not optional philosophy for people who like abstractions. It is a working rule that predicts light bending, time dilation, and the orbit of Mercury. It also predicts gravitational waves, ripples in geometry itself, later heard as faint chirps in detectors that compare distances smaller than an atom. Historically, this was not an easy idea to accept, even for experts who could follow the mathematics. Einstein's 1915 field equations replaced a familiar Newtonian force with a set of geometric relationships, and the consequences were so strange that even he doubted some of them. When the first dramatic confirmation came in 1919, during a solar eclipse expedition, it was not merely a new number on a chart, it was a new way of thinking about what space and time are, yet the theory kept surviving every new measurement, and it became the language cosmology had to speak. Cosmology takes that same rule and applies it to the whole universe. The expansion is not a special add-on, it is one possible behavior of geometry. When we say the universe expands, we're not adding a new ingredient the way we might add wind to a weather model. We're asking what the field equations allow when the matter distribution is, on average, smooth. The answer is that a changing geometry is not only allowed, it is generically expected because a static universe is a fragile special case. To make that behavior precise, we need a tool that sounds abstract but acts like a ruler. We need the metric. A metric is the rule for converting coordinate differences into physical distances and times, and it does so without caring how you label the map. It tells you what counts as 1 meter between two events, and what counts as 1 second along a world line. If you want a plain language version, the metric is the conversion table between labels on a map and what a traveller actually measures. Coordinates are labels, not measurements, and that is more than a technicality. A coordinate grid can be stretched, warped, or chosen in many ways, while the metric encodes what observers actually measure with rods, clocks, and light signals. In relativity, you can change the labels dramatically and leave the physics untouched. So the metric is the part that refuses to be fooled. This distinction matters because you can make a map look dramatic without changing the terrain. You can draw Greenland huge on a Mercator projection, and the ice does not grow. In relativity, coordinates can be just as misleading, and the metric is the thing that stays honest when the drawing style changes. In flat space, the metric is simple and familiar, and distances follow the Pythagorean rule. In curved space-time, that rule changes, and the metric carries the change in a compact testable form. It tells you how to compute the interval between events, the quantity that all observers agree on, even when they disagree about space and time separately. Even in everyday life, we use different metrics without naming them, and our brains switch between them automatically. A city block distance counts turns and intersections, while a straight line distance ignores them. In physics, the metric is not a convention like that. It is a physical field that can vary from place to place and time to time. When cosmologists say space expands, they mean the metric changes with time in a specific symmetric way. The distance between two fixed coordinate points can grow, even when nothing is moving through anything. This is where the container intuition fails most dramatically. Nothing needs to move through an external void for distances to increase. The measuring rule itself evolves, and that evolution is what we mean by expansion. If you want a visual, imagine a faint grid drawn across a dark screen, almost like chalk lines on black glass. The galaxies are bright dots pinned to the grid intersections, and the grid lines slowly separate as if the screen itself were breathing. The dots do not crawl across the lines, yet the gaps between them widen, and the pattern stays statistically the same. To connect this to observation, we return to what Redshift implied in Chapter 1. Light's wavelength stretches because the geometry it travels through changes while it travels. Think of a wave crest leaving a distant galaxy like a ripple moving across a flexible sheet. If the sheet stretches while the ripple is in transit, the spacing between crests increases by the time it arrives. The light has not lost energy to a substance. It has been carried through an evolving geometry that changes the scale of the wave. That stretching is not a friction effect and not a medium stealing energy. It is a geometric statement. The metric at reception differs from the metric at emission, and the wavelength records that difference like a timestamp. In general relativity, even the bookkeeping of energy can be subtle on cosmic scales, and that subtlety is not a loophole. In a small laboratory, energy conservation is crisp because time translation symmetry is crisp, and the laws look the same from one moment to the next. In an expanding universe, the global notion of a single conserved energy for light is not as straightforward, and Redshift is one place we see that tension. The next piece of the toolkit is the scale factor, written as AT. It is a single function of cosmic time that captures uniform expansion. Cosmic time here is not your wristwatch time, and it is not tied to any one planet's orbit. It is the time measured by observers who, on average, ride with the expansion and see the universe as isotropic around them. In that special frame, the universe has a natural clock, and ATIS describes how the spatial part of the metric changes with that clock. The scale factor does not say where the universe sits. It does not point to an edge. It tells how typical distances between co-moving points change with time, and it does so in a way that can be compared to data. Co-moving coordinates are designed to ride with the cosmic flow. In these coordinates, galaxies participating in the expansion keep roughly fixed coordinate positions, even as the proper distances between them grow. This is not a claim that galaxies are nailed in place by some cosmic lattice. It is a choice of description that matches what we see on the larger scales, where the universe looks statistically uniform. When you average over clusters and voids, you can define a smooth flow, and co-moving coordinates move with it, like choosing to measure a river by markers painted on the water rather than markers on the shore. That sounds like a trick until we separate two kinds of distance, and we keep them separate with discipline. Proper distance is what you would measure with rulers at one cosmic time. Co-moving distance is the coordinate separation. Proper distance is the right now distance, the one you would get if you could freeze the universe at a moment and lay down a chain of meter sticks. Co-moving distance is the label distance that stays fixed for objects carried along by the expansion, and it is the convenient bookkeeping distance for cosmology. Proper distance equals the scale factor times co-moving distance for the simplest homogeneous models. If AT grows, proper distances grow, even if co-moving coordinates stay constant. That relationship is deceptively simple, and it hides a deep idea about how uniform change can be. The universe can evolve in a way that is smooth enough that every large-scale ruler is effectively rescaled by the same factor. When that happens, you can track the change with one function, and that function becomes the heartbeat of cosmology, quiet, persistent, and measurable. So galaxies can be at rest in co-moving coordinates while the distance between them increases. Their local neighborhoods can be calm while the large-scale separation grows, and that coexistence is one of the most important mental adjustments in the chapter. If you zoom in on a galaxy like the Milky Way, you see stars orbiting, gas clouds collapsing, and spiral arms shearing. None of that looks like a smooth expansion, because local gravity has won there and has built bound structures. Expansion is a large-scale behavior, not a local wind that tugs on atoms or loosens the bolts in a bridge. This is not a claim that galaxies never move. Local gravity still pulls, binds, and collides, and galaxies have peculiar velocities on top of the Hubble flow. Expansion dominates only when we average over scales large enough that the lumpy details blur into a simpler pattern. On the scale of the solar system, the binding is overwhelming and the metric looks almost static. On the scale of galaxy clusters, Gravity still competes strongly, and the story becomes messy with infall, mergers, and virialized motion. On the scale of hundreds of millions of light-years, the smooth description begins to work, and the expansion becomes the main trend. The Hubble, Lemaitre law becomes less mysterious in this language. Recession speed is not a rocket speed through space, it is the time rate of change of proper distance. When you hear speed, your mind imagines an object moving past a lamppost, and it imagines one shared notion of now. In cosmology, the lamppost is not fixed in the same way, and the distance between lampposts can change with cosmic time. The recession speed is a derivative of the metric, not a local velocity measured in a single place. That is why very distant galaxies can have recession speeds greater than the speed of light without violating relativity. No object locally outruns light. The metric changes globally, and the comparison spans regions that cannot be stitched into one inertial frame. This point is often stated, but it deserves a careful picture that respects what relativity actually claims. Each galaxy, in its own local region, can measure light passing it at c, and it can measure nearby objects moving slower than c. The superluminal recession appears only when you compare widely separated regions across an evolving geometry, where there is no single shared inertial frame and no single universal simultaneity. General relativity is careful about what speed means, and the care is the whole point. Local measurements in a small region follow special relativity, and they look familiar. Global comparisons across curved, evolving space-time do not behave like a single inertial frame, even if the numbers tempt you to read them that way. If you want a more tactile image, imagine hikers on a landscape that is slowly deforming under a heat haze. Each hiker can measure their own steps and nearby motions in a normal way, and the rules of walking do not change. Yet the distance between faraway hikers can change because the ground between them is changing, not because either one is sprinting. Now we need a model of the universe that matches the large-scale symmetry suggested by surveys and the cosmic microwave background. Homogeneous and isotropic is not exact, but it is a powerful approximation, and it is surprisingly well supported. The sky is not perfectly uniform, and the universe contains filaments, clusters, and vast voids that look like a cosmic web in deep surveys. Yet when we smooth over those structures, the statistical pattern becomes remarkably simple. The cosmic microwave background with its tiny temperature variations is a direct visual of that near uniformity, like a faintly mottled glow that still looks the same in every direction. The standard symmetric model is the Friedman, Lemaitre, Robertson, Walker picture. FLRDBus is not a guess about details. It is the most general geometry consistent with large-scale uniformity, and it provides a clean stage on which the universe's energy contents can act. This is where history quietly matters, because the idea arrived before the evidence was fully persuasive. Alexander Friedman, working in the early 1920s, found that Einstein's equations naturally allow expanding and contracting solutions. Georges Lemaitre, a few years later, connected those solutions to astronomical redshifts, and argued for an expanding universe before the idea became mainstream. Their work shows a recurring theme in cosmology. Mathematics sometimes opens a door, and observation later tells us whether we should walk through it. FLRW builds the universe from two ingredients: a scale factor that changes with time, a spatial curvature parameter that describes the shape of space at a given cosmic time. In the FLRW picture, you can think of space as a stack of slices, one for each cosmic time, like pages in a book that is being gently stretched. Each slice has a geometry, and the scale factor tells how the size of that geometry changes from slice to slice. The curvature parameter tells what kind of geometry each slice has, independent of its overall scale. Curvature here is not about bending into a higher dimension, even if we sometimes visualize it that way. Curvature is intrinsic. It can be detected by measurements made within the space, using only rulers, clocks, and the behavior of light. Intrinsic curvature is the kind you can discover without stepping outside, and it has a simple operational test in lower dimensions. You can draw a triangle using the straightest possible paths, and you can measure its angles. On a flat plane, the angles add to 180 degrees. On a positively curved surface, they add to more, and on a negatively curved surface, they add to less. In 3 dimensions, the measurements are more subtle, but the principle is the same. You can compare how volumes grow with radius, how light bundles converge or diverge, or how the relationship between circumference and radius behaves for very large circles. Curvature is a property of the geometry itself, not of an embedding in a larger room. In FLRW, curvature comes in three broad options, labelled k equals +1, 0, or -1. These correspond to closed, flat, and open spatial geometries. Closed, with kethi equals +1, means positive curvature like a three-dimensional analogue of a sphere's surface. It can be finite in volume without having an edge, which is a statement about geometry rather than construction. This is one of the most counterintuitive ideas in the chapter, so it deserves a slow visual that lingers. Imagine walking in a straight line on Earth and never encountering a boundary, yet eventually returning to your starting point. The surface is finite, but it is unbounded. A closed three-dimensional space generalizes that idea, though our brains strain because we cannot step above it to look. Flat with kesa equals 0 means Euclidean geometry on large scales. It can be infinite, and it can also be finite with a more complex topology, like a video game world that wraps around without warning. A flat universe is the one that matches our everyday geometry, at least locally, and it is the one our measurements currently favour. Parallel lines behave as expected, and the Pythagorean rule holds in the spatial slices. Yet even flatness does not settle the question of size, because topology can make a flat space wrap around in ways that still have no edge and no external container. Open, with k equals -1, means negative curvature like a saddle shape extended to 3 dimensions. It is typically infinite, and distances grow faster with radius than in flat space, changing how volumes and light cones behave on the larger scales. Negative curvature has a distinctive feel in the mathematics, and it has a distinctive consequence for paths. Geodesics that start out parallel tend to diverge, and the available room grows quickly as you move outward. In an open universe, the geometry makes large-scale separation easier, as if space has extra spread built into it. The key point is not which option is true. The key point is that none of them require an outside to make sense. Geometry can be complete without an external container, because completeness is defined by internal measurements and internal consistency. This is where the original question begins to loosen its grip. Into what? Assumes that space is like a gas expanding into a vacuum chamber. In the relativistic picture, the universe is the chamber, and the question becomes operational. What measurements could ever reveal an outside if the geometry is already complete? This is where analogies help, but only if we treat them like guardrails rather than maps. They keep intuition from crashing, but they do not tell the full story, and they can smuggle in assumptions. A good analogy gives you one correct relationship and then stops. A bad analogy invites you to import extra features that are not part of the physics, like edges, centers, or surrounding air. In cosmology, those extra features can be seductive, because we are hungry for pictures that feel like everyday objects. The balloon surface analogy is the most common guardrail. Imagine a two-dimensional world on the surface of an inflating balloon. Distances between points on the surface grow as the surface expands, even though the points do not need to travel across the rubber. In a visual sequence, you can see it clearly, and the simplicity is the point. Dots drawn on rubber drift apart as the rubber stretches, and every dot sees every other dot receding. No dot is special, and there is no privileged center on the surface itself, only a changing scale. For the two-dimensional inhabitants, there is no direction on the surface that points to an outside. There is no edge on the surface. The geometry they measure is self-contained, and their laws of motion can be written entirely in terms of what happens within that surface. If those inhabitants build triangles and measure angles, they can infer curvature without ever leaving their world. If they send light signals and time the round trips, they can define distances without needing a view from above. Their physics is internal, and their space is whatever their measurements reveal, nothing more and nothing less. The analogy earns its keep by separating expansion from motion through an external space. Points can stay put on the surface while their separations increase, and that is the conceptual move we need. It also helps explain why every observer can see the same pattern of recession. On the balloon, each dot sees other dots moving away, and the farther dots recede faster. That is the geometric heart of the Hubble-Lemaitre law, expressed in rubber and ink. But the analogy also misleads if we take it too literally, and the mislead is predictable. The balloon uses a higher dimensional embedding space that the surface does not need. Our universe does not require a surrounding room in the equations, and the mathematics never asks for one. The embedding space is a crutch for our three-dimensional imagination, not a demanded feature of the theory. In FLRW, the geometry is defined intrinsically, and the mathematics never asks what it is bending into. If you can compute distances and times within the geometry, you already have the physics you need. It also misleads because the balloon has a center in the embedding space, and our universe does not have a center in the Ferrou description. Expansion is not a blast from a point, and it is not an explosion with debris flying into emptiness. A center appears only if you insist on looking from the outside, which the inhabitants of the surface cannot do. In the same way, a cosmic center is not part of the internal description that matches observations. Every comoving observer can treat themselves as central in the sense that the large-scale universe looks isotropic around them, and that symmetry is the clue, so we keep the lesson and drop the baggage. Expansion can be intrinsic. Finite can mean unbounded. Outside can be a question with no operational meaning, even if the words feel natural in the mouth. At this stage, space stops being a substance like ether, and it also stops being empty nothingness. In general relativity, space is geometry. Geometry is a field with dynamics. That word field is important because it carries a promise of lawfulness rather than metaphor. Fields have equations of motion, and they can store information about how they change from place to place. The electromagnetic field is not a material fluid, yet it has energy, momentum, and waves that can be detected. Space-time geometry plays a similar role, though it is more fundamental because it defines what distance and duration mean in the first place. This shift also changes what it means to ask where things are, and it changes what it means to compare now across the cosmos. Location becomes relational, tied to the metric and to the paths objects follow. Even the idea of simultaneous events becomes dependent on the slicing of space-time into cosmic time, and that dependence is not a mistake, it is part of the structure. The universe is not just bigger or smaller, it is organized by the way geometry makes comparisons possible. That raises a sharper version of the central question. If expansion is geometry changing, what makes geometry change in one direction rather than another? In Newtonian thinking, motion needs a force, and expansion feels like motion. In relativistic cosmology, the changing scale factor is not arbitrary, and it is not a free choice of coordinates. It is governed by equations, and those equations connect directly to what the universe contains. The equations are not optional add-ons either. They are the same Einstein field equations that explain the precession of Mercury and the bending of light. When you apply them to a universe that is homogeneous and isotropic on large scales, they collapse into a simpler set of relationships, and those relationships dictate how AT evolves. Those equations tie the behavior of AT to the contents of the universe. Energy density matters, pressure matters, even the vacuum can act like a source, and in relativity, source means stress energy, not just mass. This is where the story becomes both more concrete and more unsettling. The universe does not expand because it wants to, and it does not expand because it is escaping into emptiness. It expands because the geometry responds to stress energy, and stress energy includes forms of energy that do not behave like ordinary matter. This is the second tension beat of the story. If space is an actor, it still follows a script. We need to know what writes that script, and we need to know how the script can be read from the sky. The Friedmann equations are the script in the FLRW setting. They come from Einstein's field equations applied to a homogeneous, isotropic universe, and they translate geometry into evolution. Even without writing them on screen, we can describe their structure in a way that stays faithful. One equation relates the expansion rate to the energy density and curvature. Another relates the acceleration of the expansion to energy density plus pressure. Together, they turn the universe into a dynamical system whose future depends on what it contains, and whose past can be reconstructed from what we observe now. We do not need their full mathematical form yet, but we need their logic. The expansion rate depends on how much energy is in the universe and what kind it is, because different kinds of energy push on space-time differently. Kind matters because different components dilute differently as space expands, and the dilution is itself a geometric consequence. Matter thins out as volume grows, so its density drops roughly like AT to the -3. Radiation not only thins out, it also redshifts, so its energy density drops even faster, roughly like a T to the -4. Matter slows expansion through gravity. Radiation also slows it, and it dilutes differently as the universe grows, leaving different eras with different dominant ingredients. A component with negative pressure can drive accelerated expansion, and that possibility changes the fate of the universe in a profound way. That last phrase, negative pressure, sounds like a trick of language, but it has a precise meaning in relativity. Pressure is not just a sideways push in a fluid, the way it feels when you press your hand against a wall. Pressure is part of the stress-energy tensor, the object that tells spacetime how to curve, and it enters the cosmic evolution equations on nearly equal footing with energy density. Pressure sounds like a fluid concept, but in relativity it is part of the stress energy that curves spacetime. Pressure gravitates. It can either resist collapse or fuel expansion, depending on its sign and on the context. In everyday materials, pressure is positive, and it tends to add to gravitational attraction in the relativistic equations. That is already surprising, because we are used to pressure holding things up against gravity. In cosmology, a sufficiently negative pressure acts differently, contributing to a kind of gravitational repulsion that can make the expansion accelerate, an effect that looks like anti-gravity in the simplest description. This is where nothing becomes a technical trap. Vacuum is not always nothing in physics. A vacuum can have energy, and that energy can have pressure, and the combination can mimic a smooth component spread uniformly through space. Historically, the vacuum has been a moving target, and the shift is one of the great conceptual turns of modern science. In classical physics, empty space was simply absence, a blank stage with no properties of its own. In quantum physics, the vacuum is a state with fluctuations and structure, and it can carry an energy density that behaves, in the equations, like a uniform component filling space. In Einstein's own work, a constant energy density associated with space itself appeared as the cosmological constant. It was introduced for one reason and later abandoned. Then it returned in a new role when observation suggested accelerated expansion. The details will come later, but the conceptual seed belongs here. The vacuum can gravitate and geometry can respond to it. So the story of expansion is not a story about edges pushing into emptiness. It is a story about AT responding to the universe's energy budget, with curvature setting the geometric context and stress energy providing the driving terms. You can almost hear the shift in the question, and it is the shift that makes the mystery productive. Instead of asking where the universe is going, we ask what the universe contains and how those contents influence geometry. The expansion becomes a diagnostic tool, a way to infer invisible components from the way distances evolve, and that inference is one of cosmology's most powerful moves. We can now restate the paradox in a form that physics can answer. The universe does not expand into a place. The universe expands by changing the metric that defines distance. That restatement does not remove the mystery, it relocates it. The mystery is not where the universe is going. The mystery is why space-time evolves the way it does, and why the ingredients have the properties they have. If the metric is a field, then its evolution is a physical process with causes, and those causes are written in energy and pressure. Yet our inventory of cosmic ingredients is incomplete, and the most influential components are not the ones we can hold in our hands. That is why the question remains mysterious even after it becomes well posed, because the equations are clear, but the contents are not. We have built the minimum vocabulary to keep the next chapters honest. Metric tells us what distance means. Scale factor tells us how cosmic distances change. Curvature tells us what shape means without requiring an outside. Along the way, we have also learned a kind of humility about pictures, and that humility is a scientific virtue. The universe may be finite without edges, and it may be infinite without needing a container. The words inside and outside are not automatically meaningful when the object in question is space-time itself, and the only reliable guide is what can be measured. And we have built a new suspense line that replaces the old one. If expansion is geometry in motion, what drives that motion? What role do energy and pressure play, and why does the universe have the components it has? Next, we follow that thread into the equations and the evidence that constrain them. We ask what the universe is made of in the only sense that matters here, and we ask how we can tell. We ask what kinds of energy can make space grow faster, and what signatures those energies leave in light, structure, and time. We keep the opening hook in view, but we stop treating it as a spatial riddle. There is no edge to stand on because the geometry does not include an edge. The real question is what kind of geometry we live in and why it changes, and whether the sky is quietly telling us more than we're ready to hear. If space itself expands, how do we know? We cannot step outside and watch the grid stretch, because there is no external balcony for the universe. We only get relics that arrive as light, patterns, and statistical echoes, messages that have travelled through changing geometry. Chapter 1 gave us Redshift as a clue, and Chapter 2 gave us geometry as the mechanism. Now we test the claim the only way cosmology can. We ask whether independent measurements converge on one history of expansion and cooling, even when their instruments and assumptions differ. This is the discipline of the field, and it is also its humility. Cosmology cannot rerun the universe on demand, yet it can cross-check the same story from many angles, using relics that formed at different times. When multiple footprints point to the same path, the path becomes harder to dismiss as coincidence. The first footprint is still the simplest, and it is written directly into light. Spectral lines slide toward red in distant galaxies, and the shift grows with distance across the sky. In a spectrograph's thin rainbow, familiar atomic lines appear displaced, like a song transposed to a lower key. Those lines are not arbitrary marks, and that is why the method works. Hydrogen, calcium, and oxygen imprint specific wavelengths, fixed by quantum energy levels. When those wavelengths arrive stretched, we can quantify the stretch as redshift, Z, without guessing what the galaxy should look like. The Hubble, Lemaitre law summarizes the trend, and it turns expansion into a measurable rate. It says that, on average, recession speed increases with distance, which is exactly what an expanding metric predicts. Historically, this relationship emerged from a tension between theory and observation, then hardened into a law. Edwin Hubble's name is attached to the diagram, but Georges Lemaitre's insight matters just as much. Lemaitre connected redshifts to a dynamical universe in general relativity, and he derived an expanding solution before the story became popular. The point is not credit, but context. Expansion was not a poetic guess, it was a quantitative claim. In the early 20th century, even the scale of the cosmos was unsettled. Spiral nebulae might have been nearby clouds, or they might have been island universes. As that debate resolved into galaxies beyond the Milky Way, the redshift data suddenly had room to become cosmology. But distance is the fragile part of that sentence. Redshift is easy to measure, while distance must be built indirectly from calibrated light. That is why the distance ladder matters, and why calibration becomes a central drama for modern cosmology. A ladder is a metaphor, but it is also a warning. Each rung depends on the one below, so a small tilt at the bottom becomes a wide miss at the top. The universe does not forgive systematic error, because it multiplies it across billions of light years. We start close to home, where geometry is not yet cosmic. Parallax gives direct distances to nearby stars, and it anchors the first rung with simple trigonometry. As Earth orbits the Sun, a nearby star appears to shift against the more distant background, an angular wobble that encodes distance. For visuals, picture two snapshots taken 6 months apart, with Earth on opposite sides of its orbit. The nearby star slides slightly against a dense field of faint, fixed stars. That tiny triangle, baseline, angle, distance, becomes the most honest ruler astronomy has. In practice, parallax is exquisitely hard. The angles are tiny, measured in arcseconds and fractions of arcseconds, so the measurement demands stable telescopes and careful modelling. Modern astrometry missions, especially Gaia, have turned this rung from a shaky step into a precision platform. Gaia does more than measure positions once, because it watches stars repeatedly over years. It separates true parallax from proper motion, the star's own drift through the galaxy. That separation matters, otherwise a moving star could masquerade as a closer star. Those distances calibrate Cepheid variable stars, whose pulsation periods reveal their intrinsic luminosities. Cepheids brighten and dim with a regular rhythm, because their outer layers expand and contract in a thermal engine. The period-luminosity relation links the beat of that engine to the star's true power output. The physics is not magic, and it is not arbitrary. Cepheid pulsations are driven by opacity changes in helium ionization zones, which trap heat and then release it in cycles. Longer period Cepheids are larger and more luminous, so the timing of their pulses becomes a built-in yardstick. There is a satisfying causality to it once you see the loop. When the star compresses, it heats, and helium becomes more ionized, increasing opacity. Radiation is trapped, pressure rises, the star expands, and the gas cools until opacity drops. Then gravity pulls it back again. Cepheids extend the ladder to nearby galaxies, where parallax fails. If we know a Cepheid's true brightness, then its apparent brightness gives distance through the inverse square law. On screen, the method looks almost serene. Pinpoint stars in a spiral arm, each one a metronome of light. Yet even that serenity hides a crowded stage. In a real image, a Cepheid is embedded in a galaxy's glow surrounded by unresolved stars and dust lanes. Extracting its light curve means subtracting backgrounds, correcting point spread functions, and trusting that the calibration is stable. That step sounds clean, but dust, metallicity, and crowding can bias the result. Dust reddens and dims starlight, and it can mimic extra distance if it is not corrected. Metallicity changes a star's atmosphere and pulsation properties, subtly shifting the period, luminosity calibration. Crowding adds a quieter danger. In distant galaxies, a Cepheid may blend with nearby stars in the same pixel, making it appear brighter than it really is. That makes the galaxy seem closer than it is, and the error propagates upward. Calibration is not bookkeeping. It is the difference between a universe that expands at one rate and a universe that expands at another, with different ages and different fates. A small, systematic error at the bottom becomes a large error at the top, because the ladder amplifies it. This is why teams obsess over photometric zero points, filter curves, and detector nonlinearity. It is why they compare space-based and ground-based observations, and why they re-observe the same stars in multiple bands. The drama is technical, but the stakes are cosmic. Even the choice of wavelength becomes strategy. Infrared observations cut through dust and reduce scatter in Cepheid relations, but they introduce their own calibration challenges. The ladder is never a single measurement, it is a chain of decisions that must be audited. Type Ia supernovae push the ladder much farther. They are not identical bombs, but they are standardizable candles with remarkably consistent behavior. A Type Ia is thought to involve a white dwarf pushed toward instability, producing a thermonuclear runaway that briefly rivals a galaxy's brightness. The leading picture involves a carbon, oxygen white dwarf in a binary system, though the details can vary. Matter may be accreted from a companion, or two white dwarfs may merge. In either case, when conditions ignite runaway fusion, the star is unbound in seconds. The light curve matters as much as the peak. Brighter Type Ia supernovae tend to fade more slowly, and that correlation lets us correct their luminosities. In the data, each supernova becomes a point on a plot, yet each point began as a star's final physics experiment. Spectra provide another safety check because they reveal the supernova's identity. The absence of hydrogen lines and the presence of silicon features help confirm it is Type Ia, not an imposter. Classification is part of the measurement. Mistakes here become cosmological errors later. Supernova surveys are also exercises in patience. Telescopes revisit the same patches of sky, night after night, searching for a new point of light that was not there before. Then they follow its fading, capturing a time series that becomes a distance estimate. For visuals, the sky becomes a flipbook. A faint dot appears near a galaxy's edge, brightens over days, then slowly drains away. The camera keeps returning, as if checking a pulse, until the curve is complete enough to trust. Now the Hubble diagram becomes a test of expansion history, not just expansion today. Plot redshift against supernova distance, and the curve encodes how the scale factor changed over time. If the universe were only matter-dominated, the expansion would slow, and the curve would bend one way. The data do not match a simple slowing expansion driven only by matter. Instead, distant supernovae appear dimmer than expected in a decelerating universe, implying they are farther away. In visual terms, the points refuse to sit on the old line, and the deviation grows with redshift. This is where the story tightens. Supernovae suggest the expansion has been speeding up in the recent universe, over roughly the last several billion years. Acceleration is not a philosophical twist, it is a measured departure from deceleration in the distance, redshift relation. The historical shock is worth remembering. In the late 1990s, two competing teams reported the same unsettling result, and the agreement made it harder to dismiss. The universe was not merely expanding, it was accelerating, as if an unseen hand were easing pressure on the brakes. That hand was not visible in any telescope image, and that absence is part of the unease. The evidence was geometric, not photographic, and it relied on careful control of biases. It forced cosmology to accept a new dominant component without seeing it directly. We name the effect dark energy, and we admit what that name does. It labels a cause in the equations, not a mechanism in the world, and it keeps our ignorance honest. The term is a placeholder that says something acts like a repulsive component on cosmic scales. It tells us the expansion accelerates, while leaving open what physical ingredient produces it. It could behave like a cosmological constant in space and time, or it could evolve slowly. The supernova evidence alone does not settle the underlying nature, it only forces the effect. The second footprint is older and more global. The cosmic microwave background is a nearly uniform glow at 2.7225 Kelvin, filling the sky with extraordinary smoothness. It arrives from every direction, and it looks like the universe remembering its own heat, an afterimage of a hotter era. For visuals, imagine the sky mapped in microwaves. At first it looks like a calm, featureless sphere. Then the colour scale tightens and faint speckles emerge. Those speckles are not noise, they are the earliest measurable texture of the cosmos. The CMB is not starlight scattered by dust. It is thermal radiation released when the early plasma became neutral enough for photons to travel freely. That moment is last scattering, about 380,000 years after the Big Bang, when the universe cooled to roughly a few thousand Kelvin. Before last scattering, electrons and protons kept photons trapped in a hot, opaque fog. Photons scattered constantly off free electrons, so light could not travel far without being redirected. The universe was more like the interior of a star than the transparent space we see today. The transition is called recombination, though it is really the first stable combination. As electrons bound to nuclei, the number of free electrons plummeted, and the mean free path of photons exploded. In plain terms, the universe went from foggy to clear. After recombination, the fog cleared, and the photons streamed outward. Expansion stretched their wavelengths for billions of years, cooling them into microwaves. The same radiation that was once visible and infrared has been redshifted into a cold bath that now defines a cosmic temperature floor. The CMB's near uniformity is a clue about the early universe. It says conditions were almost the same across vast regions, with only tiny fractional differences. Yet it's not perfectly smooth, and that imperfection is the more valuable message. The mottling is tiny, about 1 part in 100,000. Those temperature anisotropies trace density variations in the primordial plasma, along with subtle velocity flows. They are the seeds that later grew into galaxies and clusters, amplified by gravity over cosmic time. We do not need heavy math to read the next layer, but we do need the physical picture. In the early universe, gravity tried to compress overdense regions, pulling matter inward. Radiation pressure pushed back. Because photons carry momentum and resist compression in a hot plasma, the result was oscillation. The plasma rang like a coupled fluid, with sound waves propagating through it, compressing and rarefying in cycles. Each wave had a characteristic scale set by how far sound could travel, before photons decoupled, a distance called the sound horizon. It is worth pausing on that phrase because it sounds abstract while being concrete. The sound horizon is literally a distance, measured in kilometers then, and in megaparsecs now. It is a ruler forged by microphysics, temperatures, densities, and the speed of sound in the plasma. Those oscillations left a characteristic pattern in the CMB. When we decompose the sky into angular scales, we see acoustic peaks. Each peak is a frozen note from a sound wave that stopped when photons decoupled, preserving a snapshot of the oscillation phase. The first peak corresponds to regions that had time to compress once, reaching maximum compression at decoupling. Higher peaks correspond to regions that completed additional half oscillations, like harmonics on a string. In the power spectrum, the universe reveals its early dynamics as a structured series of ridges. For visuals, the speckled sky dissolves into a clean graph. Peaks rise like mountain ranges, evenly spaced but not equally tall, as if the cosmos left a barcode. The narrator's job is to translate that barcode into a physical story. Cause and effect stays simple if we keep the chain intact. The peak positions tell us the geometry of space on large scales. because geometry determines how a fixed physical ruler projects onto the sky. The observed pattern points to near flatness, meaning the spatial curvature is close to zero within measurement precision. Near flatness is not merely aesthetic. In a curved universe, the same physical scale would appear larger or smaller in angle, shifting the peak locations. The fact that the peaks land where flat geometry predicts is a stringent test, because it is hard to fake across many multipoles. The peak heights tell us what the universe contains. More baryons deepen compressions and change the odd and even peaks, because baryons add inertia to the oscillating fluid. More dark matter changes the gravitational wells and shifts how oscillations grow, because dark matter clumps without feeling radiation pressure. In that sense, the CMB is a census. It measures the baryon density, the dark matter density, and the overall matter fraction, all encoded in the relative peak amplitudes. It also constrains the primordial fluctuation spectrum, telling us how lumpy the initial conditions were across scales. The CMB therefore does two jobs at once. It confirms a hot, dense early phase that cooled by expansion, and it quantifies the ingredients that shaped later structure. It also measures the cosmic inventory, including matter density and baryon fraction, with striking internal consistency. Yet the CMB also introduces limits, not just answers. It comes from a finite distance and a finite time, a spherical shell around us called the surface of last scattering. It reminds us that our view is bounded by horizons, even if the universe itself is not. There is also a subtlety in what uniform means. The CMB is uniform after we subtract a strong dipole pattern, caused by our motion relative to the CMB rest frame. That dipole is a reminder that we are not privileged, and that even our velocity becomes part of the measurement. That motion is measurable as a temperature difference across the sky, warmer in the direction we are moving and cooler behind us. It is a Doppler imprint, and it is large compared to the tiny primordial speckles. Removing it is like steadying a camera before examining fine grain. The third footprint is chemical. Big Bang nucleosynthesis happened when the universe was minutes old, not hundreds of thousands of years old. In that brief window, the expanding fireball cooled through the temperatures that allow light nuclei to form, while densities were still high enough for nuclear reactions. The timeline is fast and unforgiving. At first, protons and neutrons interconverted through weak interactions, but as the universe expanded and cooled, those reactions froze out. Free neutrons then began to decay, so the clock mattered, and expansion set the pace. A key moment is the deuterium bottleneck, and the name is almost literal. Deuterium is fragile at high temperatures, so early attempts to build it were immediately destroyed by energetic photons. Only when the universe cooled enough could deuterium survive long enough to build helium. The result is a specific mix, mostly hydrogen, about a quarter helium by mass, with traces of deuterium and lithium. That mix is not arbitrary, because nuclear binding energies and reaction rates constrain what can form before the universe becomes too cool and too dilute. Stars can change these abundances later, but some environments preserve the primordial ratios well enough to measure. We look to metal-poor gas clouds and ancient stellar populations, where later processing is minimal. In spectra, the fingerprints are faint, yet they carry the memory of the first minutes. Deuterium is the key thermometer. It is fragile and easily destroyed in stars, so a high deuterium abundance points back to a primordial origin rather than stellar manufacture. Its value depends sensitively on the baryon density and the expansion rate during nucleosynthesis, which makes it a sharp diagnostic. If baryon density is higher, deuterium is burned more efficiently into helium, leaving less behind. If expansion is faster, reactions shut down earlier, leaving more deuterium unprocessed. In that way, a simple isotope ratio becomes a probe of early universe conditions. Helium adds a second constraint. The helium fraction depends on how long neutrons survived before being locked into nuclei, and how quickly deuterium bottlenecks were overcome. That timing depends on the expansion rate, because expansion sets the clock for when reactions freeze out and when densities fall. This is why nucleosynthesis is not just chemistry. It is a fossil record of early expansion, written in nuclear binding energies and reaction networks. The observed abundances match a universe that was hotter and denser, then cooled as it expanded, with parameters consistent with the CMB's baryon density. Lithium complicates the picture, and its tension is instructive. Observed primordial lithium in old stars appears lower than simple nucleosynthesis predictions, suggesting astrophysical depletion or missing details. Even here, the footprint is useful because it tells us where our models are brittle. The fourth footprint is structure on the larger scales. Galaxies are not sprinkled randomly, and they are not arranged in perfect order. They form a cosmic web of filaments, clusters and voids that grew from the small initial perturbations, like frost spreading along invisible lines. In visuals, the web is almost anatomical. Filaments stretch like tendons between dense knots, while voids open as dark cavities where few galaxies live. The pattern is not designed, yet it has a coherence that invites explanation. Large surveys map this web in 3 dimensions using redshifts as distance proxies. Each galaxy's spectrum provides a redshift, and the redshift becomes a coordinate along the line of sight. When millions of these points are assembled, the universe becomes a statistical object we can measure. To the eye, a survey map looks like a city at night viewed from above, except the streets are millions of light-years long. Dense regions glow with points, and empty regions gape like missing neighborhoods. The structure is not a metaphor. It is matter responding to gravity over time. The statistics of clustering reveal how fast structures grew. Growth depends on the expansion history, because expansion competes with gravity, diluting matter and stretching separations. If expansion dominates, growth slows, and if gravity dominates, growth accelerates into larger clumps. Inside that web is another standard ruler. The same early universe sound waves that shaped the CMB also set a preferred scale in the matter distribution. That scale is baryon acoustic oscillations, imprinted as a slight excess of galaxy pairs at a characteristic separation. The idea is subtle but concrete. In the early plasma, sound waves pushed baryons outward from overdense centers, creating a shell at the sound horizon. When photons decoupled, the pressure support vanished, leaving a faint ring-like preference in where matter ended up, later visible as a Bow bump in correlation functions. Bow works because the ruler length is calibrated by early physics, and that calibration is anchored by the CMB. We can measure its apparent size at different redshifts, both across the sky and along the line of sight. That lets us infer distances and expansion rates across cosmic time, independent of supernova methods. Because BAO is a statistical feature, it is robust against many local astrophysical complications. Individual galaxies can be messy, but the ensemble carries the imprint cleanly. The ruler is faint, yet it repeats across the sky, and repetition is the ally of precision. Now the convergence becomes the main beat. Redshift surveys give a broad expansion map, and they chart how clustering evolves with time. Supernovae trace late-time acceleration through luminosity distances. The CMB fixes early conditions and geometry, and it calibrates the sound horizon scale. Nucleosynthesis checks the early expansion clock through nuclear abundances. Bow ties early physics to late structure by carrying the same ruler from the plasma era into the galaxy distribution. Each method speaks a different dialect, yet they tell a compatible story. These lines of evidence are not copies of each other. They use different instruments, different astrophysics, and different sources of error, which is exactly why their agreement matters. Yet they point toward one coherent model, an expanding universe that has cooled from a hot beginning. Coherence in science is not a feeling, it is a constraint. When independent relics agree, the allowed histories narrow, and the remaining freedom becomes meaningful. The universe is not just expanding in a vague sense, it expands in a way that obeys specific numbers. That coherence is not the end of the mystery, it sharpens it. If expansion is real and measurable, then we must also accept what expansion implies about what we can never see and what we can never test directly. Introduce the first horizon carefully. The particle horizon is the maximum distance from which light could have reached us since the beginning, given the finite age of the universe. It defines the observable universe, not because of technology, but because of finite light travel time through an evolving scale factor. On screen, the particle horizon is not a wall. It is a sphere centered on us, expanding as time passes, because more light has time to arrive. The sphere is not special because we are special, but because any observer would draw the same sphere around themselves. Observable does not mean all that exists. It means all that has had time to affect us, through signals traveling at light speed or slower. Regions beyond the particle horizon may be real, and they may be similar, but they are causally disconnected from our present observations. There is also an event horizon in an accelerating universe. If acceleration continues, some galaxies we see today will eventually become unobservable, even if they are bright and even if we wait forever. Their future light will never reach us, because space between us expands too quickly for the photons to make headway. This is one of the strangest consequences of acceleration. The observable universe can effectively shrink in terms of what remains in causal contact. Even while the particle horizon grows, the sky becomes a record of what once was reachable, not a promise of what will remain reachable. Imagine a far galaxy sending a steady stream of photons, each one racing toward us at light speed. In a strongly accelerating space-time, the distance those photons must cross can grow faster than their progress. The result feels paradoxical. Light moves, yet never arrives. Horizons change the emotional tone of the question. The universe can be larger than our cosmic bubble, perhaps vastly larger, and our best maps may still be local. The absence of an edge in our view is not proof of infinity, and the presence of a horizon is not a boundary in space. A horizon is a boundary in time and causality. It is the limit of communication, not the limit of existence. That distinction is easy to say, yet hard to internalize, because our intuitions evolved in small, slow worlds. This returns us to the central question in a more disciplined form. Expansion is not inferred from one clever analogy about balloons, though analogies can help us start. It is inferred from multiple relics that agree on one evolving geometry, and that agreement survives increasingly precise measurement. Still, agreement does not mean closure. The same data that confirm expansion also expose tensions, and tensions are where new physics sometimes hides. The measured value of the Hubble constant depends on method, and the difference has resisted easy fixes. Local distance ladder measurements using Cepheids and supernova prefer a higher H0. Early universe inferences from the CMB prefer a lower H0 within the standard model, because the CMB constrains a combination of parameters that implies a specific present expansion rate. The mismatch is not enormous, but it is persistent. One way to picture the tension is as two clocks that should agree. The early universe sets a clock through the sound horizon and the CMB's peak structure. The late universe sets a clock through calibrated brightness and observed recession, and the two clocks tick slightly out of sync. This is not a trivial bookkeeping dispute. A higher H0 implies a younger universe for the same model, and it can imply different behavior of dark energy or other components. The disagreement could be hidden systematics, or it could be new physics that changes early expansion or the sound horizon scale. Researchers therefore interrogate every rung again. They test Cepheid metallicity corrections, supernova population drift, dust laws, and selection biases. They also test the CMB analysis pipeline, foreground subtraction, and the assumptions of the baseline cosmological model. They also seek alternative calibrators that still fit the same ladder logic. Different standard candles and geometric methods can check whether Cepheids are the weak link, or whether the tension is deeper. The goal is not to win an argument, it is to locate the source of the discrepancy. Acceleration raises a deeper puzzle than a number disagreement. In the Friedmann equations, acceleration requires a component with sufficiently negative pressure, which is a technical statement with an intuitive translation. It means the energy component does not dilute like matter, and it contributes to pushing the expansion rate upward. Dark energy fits as a term, but its physical identity remains unknown. It could be vacuum energy, it could be a field that evolves slowly, or it could signal that gravity behaves differently on the larger scales. The chapter does not resolve the mechanism, because the evidence is about the effect. We can say what dark energy does without pretending we know what it is. It acts smoothly across space, it dominates the energy budget today, and it changes the fate of distant regions. It makes the universe not just expand, but expand faster, and it makes horizons more consequential. The chapter's final beat is a controlled unease. The footprints are clear enough to trust the expansion story, and they are diverse enough to make it hard to dismiss. Yet the story points beyond itself, toward horizons, missing ingredients, and limits on what any observer can confirm. So we end where the hook began, but with firmer ground. There is no edge to stand on because the evidence describes geometry, not a growing object in a larger room. The universe does not expand into nothing, because outside is not part of the model. It expands by changing the metric that defines distance, and the data force us to take that seriously. When we say space expands, we mean that the rule for converting coordinates into physical separations evolves with time. The footprints, redshifts, background radiation, abundances and structure agree that the rule has changed. Next, we follow the implications. If the observable universe is only a patch, what can we infer about the whole, and what can never be inferred? If dark energy drives acceleration, what is it made of, and why now, in this era rather than another? The footprints lead forward, and the paradox returns with sharper teeth. We have evidence that distances grow and light records that growth. Now we face the harder step, interpretation of what the beginning actually means. The central question keeps returning in a new disguise, because our intuition keeps demanding a stage with walls. How can the universe expand with no external space and no edge to expand into, if expansion feels like motion? Even the word expand drags in a mental picture of pushing outward, as though space were a gas in a container. The most persistent misconception is also the most intuitive, because it borrows imagery from ordinary life and everyday explosions. The Big Bang is pictured as a bomb going off at one location, with a shock front racing outward. On screen, that image is irresistible, an incandescent sphere, a bright rim and darkness beyond. In that picture, matter flies outward into a pre-existing emptiness, like shrapnel into a dark room with silent corners. The question, where is the centre, feels unavoidable, because explosions have centres and debris has trajectories. We imagine a privileged point where the action started, and we imagine a boundary where the action has not yet arrived. But the equations that match the sky do not describe an explosion in space. They describe space itself evolving from a hotter, denser state, with matter and radiation carried along by changing geometry. The difference sounds grammatical, yet it changes what questions are even meaningful. That difference is subtle in words, yet dramatic in meaning, because expanding space is not a substance flowing outward. It is a change in the metric relationships that define distance, duration, and the paths light can take. In general relativity, the metric is not a backdrop, it is the object being solved for. Big Bang is not a place in the universe. Big Bang is a description of the universe's early conditions, inferred from how the cosmos behaves now and from the relics it still carries. It is a reconstruction, built from redshifts, background radiation, and the chemistry of the first elements. When cosmologists say the universe was smaller, they mean the scale factor was smaller. They do not mean the universe sat inside a larger room, surrounded by emptiness, waiting to burst. The size is relational, how far moving points are from each other at a given cosmic time. To make that less abstract, imagine a grid painted on space itself. No walls, no edges, just a pattern of squares. As the scale factor AT changes, the spacing between grid lines changes everywhere at once, even if the paint never slides. The visual is calm rather than violent, like a fabric slowly tightening or loosening under a uniform pull. In a visual sense, the grid is the stage and the ruler at the same time. If the grid stretches, every measured separation changes, and nothing needs to move through an outside medium. The galaxies can remain at rest in comoving coordinates while their proper distances still grow. In the FLRW framework, homogeneity and isotropy are built into the geometry from the start. No comoving observer is privileged, and no comoving location is the origin, because the symmetry forbids an origin. The mathematics encodes that symmetry so strictly that a centre would be a violation, not a hidden feature. Homogeneity means that, on large scales, the universe has the same average properties at every location. Isotropy means it looks statistically the same in every direction. Once local clutter is averaged away and nearby structures are treated as noise. The key phrase is on large scales, because the universe is lumpy up close, yet smooth in the cosmic average. Those are not philosophical preferences, and they are not chosen because they sound elegant. They are hypotheses about the large-scale universe, tested by surveys, by the CMB, and by the distribution of galaxies across immense volumes. The remarkable fact is not that the assumptions exist, but that the sky keeps cooperating with them. Every observer sees other distant galaxies receding on average. That symmetry is not a trick of perspective, it is the model's core assumption, and it is tested against the sky with relentless statistics. When the data disagree, cosmologists do not argue with the universe, they revise the model. When we map redshifts across millions of galaxies, we see a consistent pattern of expansion. The pattern is not centered on us, because any co-moving observer would measure the same large-scale flow, aside from local gravitational peculiarities. Those peculiar velocities, motions inside clusters and along filaments, are real, but they ride on top of the global trend. Even the language of recession needs careful handling, because galaxies are not necessarily moving through space like bullets. At sufficiently large scales, the dominant effect is that the distance defined by the metric increases, and light accumulates redshift along the way. In that sense, the wavelength is stretched with the geometry, as though the photon were being carried by the expanding grid. So what does everywhere mean without becoming wordplay? It means the hot, dense state was not localized within space. It was the state of space, including the matter and radiation filling it. Everywhere is not a point smeared out. It is a condition shared across the whole slice of cosmic time. If you could hover above a young universe in a godlike diagram, you would not see a fireball expanding into blackness. You would see the entire canvas glowing, then cooling as the canvas stretches, with no privileged point where it began. The brightness would be uniform enough to feel eerie, like a light with no lamp. The glow is not metaphorical in the early plasma epoch, because the universe was literally filled with thermal radiation. Photons were abundant, energetic, and continually scattered, so the cosmos behaved like a fog of light. In that fog, darkness is not outside. It is simply not yet a meaningful category. Pick any two co-moving points and run the clock backward. Their proper distance shrinks with AT, even if their coordinates stay fixed, because the coordinate labels are attached to the expanding grid. This is why motion can be the wrong mental verb, even though distances undeniably change. That distinction matters, because coordinates can be chosen many ways, while proper distance is physical. Proper distance is what a ruler would measure at one cosmic time if you could freeze the expansion and lay the ruler down. In practice, we infer it from light travel, redshift, and an assumed cosmological model. Run the clock backward far enough, and all large-scale separations become small. The universe becomes denser because the same contents occupy less volume, and radiation becomes more energetic as wavelengths are compressed. Temperature rises because the photon spectrum shifts upward, not because heat is being poured in from outside. As the volume shrinks, number densities rise and collision rates increase. Photons scatter more frequently off charged particles, and the universe behaves less like empty space and more like a hot plasma with collective behavior. The plasma supports pressure waves, and those waves leave imprints we can still measure. In that plasma, electrons, protons, and light are locked together by electromagnetic interactions. The mean free path of a photon becomes tiny, so seeing across the universe is impossible in the usual sense. The cosmos is bright, but it is also opaque, like looking into the interior of a star. That statement does not require an edge. It does not require an outside. It only requires a metric whose scale changes with cosmic time, so that the same co-moving region corresponds to different physical sizes. The intuition shifts from stuff flying outward to relationships changing everywhere. The metric is the rule that tells spacetime how to measure intervals, how far, how long, and how light cones tilt. In FLRW, that rule is simple enough to write down, yet rich enough to explain much of what telescopes record. It turns the expansion into geometry, and geometry into a measurable history. It is also why the tiny point image misleads so reliably. A point is a location inside a larger geometry, while the Big Bang is about the geometry itself and its changing scale. The model is not saying everything was at one address, it is saying all separations were once much smaller. A point also implies a surrounding place where the point sits, and a direction outward from it. The early universe, as described by FLRW, offers neither a surrounding container nor a preferred outward direction, only a global change in scale. If you insist on an outside, you're asking for an extra structure the model does not contain. The balloon analogy helps only if we keep its one lesson. Distances can grow intrinsically without motion through an external medium, and the geometry can expand while the inhabitants remain at rest in their coordinates. The analogy is a training wheel, useful until it starts steering you. On the balloon surface, dots can separate even if the rubber carries them passively. No dot is the center of the surface, even though the surface expands, and every dot sees others receding. If the dots could measure redshift, each would conclude the same law of expansion. The analogy fails if we import its extra baggage. The balloon has an embedding space and a center, while FLRW needs neither, and the observable universe is not the surface of a larger object. The center of the balloon is not a place on the balloon, and that mismatch is where the analogy quietly breaks. Cosmologists use analogies cautiously, because the mind clings to the wrong parts. The useful part is the changing distance rule, not the existence of a surrounding air-filled room that the balloon expands into. The moment the analogy gives you a new outside, it has already started lying. If there is no center, why does the word singularity appear at all? Because classical general relativity, when extrapolated backward, hits a limit where the mathematics refuses to stay finite. The term is a signal flare in the equations, not a photograph of a physical object. Historically, this was not a casual word choice. In the mid-20th century, mathematicians like Hawking and Penrose showed that, under broad conditions, spacetime geodesics become incomplete, even without assuming perfect symmetry. Their work reframed singularities as generic features of classical gravity, not quirks of idealized models. Their theorems did not claim a literal point you could point to with coordinates. They claimed something more austere. If gravity behaves classically and energy conditions hold, then some past-directed paths cannot be extended indefinitely. In other words, the classical story ends, even if you try to avoid special coordinates. Geodesic incompleteness is a technical phrase with a plain meaning. It says that tracing the paths of freely falling observers backward, the classical description ends after a finite amount of proper time, as though the story runs out of pages. The ending is in the description, not necessarily in reality. In many FRW solutions, as AT approaches zero, density and curvature scalars diverge. The math signals that the classical description breaks, because the quantities that measure gravitational intensity become unbounded. This is not just big numbers, it is the loss of a well-defined continuum. Curvature scalars are coordinate-independent measures of how strongly spacetime is bent. When they blow up, it is not a mere artifact of a bad coordinate choice, but a genuine failure of the smooth model. The warning is geometric, not linguistic. A singularity in this context is not a confirmed physical object. It is a warning that the theory is being pushed beyond its domain, like using a map far beyond the region it was designed to cover. The responsible move is to stop extrapolating with confidence, not to declare victory over mystery. It does not mean the universe was literally an infinitesimal dot floating in darkness. It means the equations stop giving reliable, finite answers, and the classical continuum picture stops being trustworthy. The dot is a cartoon, and cartoons can be dangerously persuasive. In practice, it is like following a map until the paper ends, then refusing to invent roads beyond the edge. The end of the map is real, but it is not the end of the landscape, and it may not mark a cliff. It marks the place where your tool stops working. This is a crucial distinction for the central question. Expand into nothing assumes a background nothingness, but the model has no background stage and no external coordinate grid. The question smuggles in a theatre that general relativity does not provide. Instead, the model says space-time geometry is the arena and the actor. If the actor's script fails at early times, we should not pretend we know the scene, the props, or the lighting. We can describe the later acts with confidence, while admitting the opening pages are missing. So we ask what the singularity talk does allow us to say. It allows us to say the early universe was extremely hot and dense, because later evidence points back to those conditions. The evidence is not a single clue, but a converging set of independent measurements. We can say this because we observe the cooled remnants of that heat today. The universe carries fossils, photons, light elements, and large-scale patterns that remember earlier conditions in measurable, quantitative ways. Each fossil is a constraint, and together they form a tightly interlocked narrative. It allows us to say the universe has been expanding and cooling for a long time. It does not tell us the literal first instant, and it does not guarantee that first is even the right word. First implies a sequence that may not exist in the way we imagine. Even the word instant becomes slippery near the limit because time is not an external stopwatch in general relativity. Time is part of the geometry that is evolving, and the geometry is what becomes uncertain. When the clock is part of the machine, you cannot assume it ticks the same way under all conditions. The phrase "the beginning of time" is often used as a shortcut. It can be meaningful, but it can also hide several different claims that sound similar in conversation. The narration has to slow down here, because the words are familiar while the concepts are not. One claim is operational and modest. Our cosmic time coordinate tied to moving observers cannot be extended past some boundary because the classical space-time description ends. This is a statement about what the model can represent, not about what reality must be. Cosmic time is defined by the clocks of observers who see the universe as homogeneous and isotropic around them. It is a convenient slicing of space-time, not necessarily a fundamental one, and it can fail when the assumptions fail. In a highly quantum or highly anisotropic regime, cosmic time may not be the right clock. Another claim is metaphysical and stronger. Time itself came into existence, so before is not a well-defined relation, because before presumes a timeline on which events can be ordered. This is where everyday grammar starts to mislead, because it treats time like a container. Cosmology has to separate what the equations demand from what language suggests. Before is a time-ordering word, and time may be part of what began, so the grammar can quietly smuggle in an assumption. The question can be meaningful in one framework and meaningless in another. In general relativity, time is not an external parameter. It is part of the dynamical structure, linked to the metric and to matter content. So changing matter changes the available notions of time. Different observers can slice spacetime differently, and the theory allows that flexibility. Matter tells spacetime how to curve, and curvature tells matter how to move, yet both are expressed through the same geometric language. When the geometry becomes uncertain, our usual causal story becomes uncertain too, because cause and effect rely on spacetime structure. Causality is not a separate rule pasted on top, it is built into the light cones. If the classical spacetime description fails at early times, then the usual causal ordering may fail too. The question, what happened earlier, may lose meaning, not because we dislike the question, but because the framework that defines earlier dissolves. The loss is conceptual, like trying to define up without gravity. That loss of meaning is not a rhetorical trick. It is a consequence of how general relativity ties time to the structure of space-time, rather than treating it as a universal background shared by all possible worlds. The universe is not evolving inside time. Time is one of the things evolving. Still, we should not pretend there is only one interpretation. Some models treat the Big Bang as a boundary of space-time, where the coordinate reaches a limit but the concept of outside is not required. The boundary is a limit of extension, not a physical wall. In those pictures, the beginning is like the South Pole on Earth. There is no point farther south, yet the pole is not a wall. The coordinate reaches a limit and the question changes form rather than being answered by a location. You can walk to the pole, but you cannot walk past it in the same direction. Other models treat it as a transition from a prior phase. In those pictures, before exists, but it is not described by classical FLRW, and the prior phase may have different effective laws. The same observational relics must still be matched, which is where many ideas become fragile. There are bouncing cosmologies where contraction precedes expansion. There are emergent scenarios where expansion begins from an earlier quasi-static state, so the hot phase is not the absolute start. These ideas are not mere speculation, but they are constrained by the same sky we use to test everything else. In a bounce, the scale factor decreases, reaches a minimum, and then increases again. The challenge is not drawing the curve, but finding stable physics that avoids singular behavior while matching observations, including the CMB's detailed statistics. A successful bounce must also explain why the universe is so smooth after the rebound. In emergent scenarios, the universe can linger in a slowly changing state, then enter the hot expanding phase. The promise is extra time for causal processes, though the microphysics must still be specified and must not contradict later relics. The narrative becomes longer, but the constraints become tighter. There are also proposals where time is not fundamental and emerges from deeper quantum degrees of freedom. In that case, before becomes a category error, like asking what is north of the North Pole. The point is not to be clever, but to respect what the mathematics may be telling us. This is not a retreat into philosophy. It is a statement about what our best tested equations can and cannot extend, and about how far extrapolation can be trusted. The discipline is to keep the mystery precise rather than letting it become vague. The boundary is often labelled with a number that sounds precise. The Planck time is about 10 Ra 43 seconds after the extrapolated start, a scale so small that ordinary intuition cannot grip it. It is not a measured timestamp, It is a signpost built from constants. That number comes from combining constants: the speed of light, Newton's gravitational constant, and Planck's constant. It marks the scale where quantum effects of gravity are expected to matter, because those constants set the natural units of spacetime itself. When you combine them, you get a regime where neither quantum theory nor gravity can be ignored. At that scale, quantum effects of gravity are expected to matter. The energy densities approach the Planck density, and spacetime itself should fluctuate, meaning the classical idea of a smooth metric becomes an approximation. The phrase approximation is doing heavy work here, because it may mean the geometry is not even well defined in the usual sense. The phrase spacetime fluctuates is easy to say and hard to picture. It suggests that the smooth continuum of geometry becomes more like a restless quantum system, with uncertainty in curvature and perhaps even in topology. If topology can change, then where becomes a moving target, not a fixed stage. Classical general relativity treats geometry as smooth. Quantum theory suggests smoothness breaks down when actions approach h and lengths approach the Planck length, because localization of energy becomes inseparable from gravitational back reaction. The act of probing the regime becomes part of the regime, and measurement stops being passive. At such scales, the very idea of a sharply defined event may blur. If you try to localize energy into a tiny region, gravity responds strongly, potentially forming horizons that complicate measurement and limit what position can mean. The universe may hide its earliest details behind the structure of its own laws, so our predictive power fades as we approach that era. We can evolve equations backward, but the confidence interval grows into a fog, because the missing physics is not a small correction. It is a missing chapter, not a missing footnote. That fog is not ignorance of everything. It is ignorance of the specific mechanism that replaces classical spacetime, while still respecting the successful predictions we can test later, from nucleosynthesis to the CMB. The later successes are the rails that keep speculation from drifting into fantasy. The honest statement is not that we know what happened at t=0. The honest statement is that our classical model becomes incomplete, and the word zero may be a coordinate label rather than a physical moment. A label can be useful without being literal. Yet the Big Bang model is not only about the first instant. It is about a long early phase where the universe was hot, dense, and expanding, and where well-understood physics leaves measurable fingerprints. The power of the model is that it connects a remote past to data we can collect now. During that phase, the universe passed through well-understood regimes: radiation domination, then matter domination, each with a characteristic relationship between expansion rate and energy density, and each with different consequences for structure growth. The expansion rate is not arbitrary, it is tied to what the universe contains. In radiation domination, pressure matters, and the expansion rate is rapid. In matter domination, gravity has more time to amplify small density contrasts, so the cosmic web can emerge from tiny initial irregularities. Those irregularities are small in amplitude, yet they are everything, because they become galaxies. We have strong evidence for that phase from the cosmic microwave background and primordial abundances. Those relics anchor the story well after Planck time, in epochs where laboratory-tested physics can be applied with confidence. The universe becomes a laboratory, and the lab results are written across the sky. Primordial nucleosynthesis, for example, depends on the competition between expansion and nuclear reaction rates. The observed helium and deuterium abundances match a universe that was once a few minutes old and extremely hot, with a specific baryon to photon ratio. If the expansion had been faster or slower, the nuclear outcomes would be measurably different. That match is not just qualitative, it is sensitive to the number of light particle species and to the expansion rate, so the early universe becomes a kind of cosmic laboratory for particle physics. In a sense, the cosmos performs an experiment at energies we cannot reproduce on Earth. The cosmic microwave background is even more visually haunting. It is a nearly uniform bath of photons, now cooled to about 2.7 Kelvin, arriving from all directions like a whisper from a younger cosmos. The photons are ancient, yet they arrive with the steadiness of a present tense signal. On screen, the CMB is often shown as a mottled oval map, its colours exaggerated to reveal microkelvin variations. Those tiny variations are not noise, but a record of sound waves in the primordial plasma. They are the frozen ripples of pressure and gravity, captured at the moment the fog cleared. So the chapter's task is to reframe beginning. without losing what the evidence actually supports. The beginning is a limit of extrapolation, not a pinpoint, and the evidence speaks most clearly about eras after that limit. The mystery is real, but it is bounded by what we can test. This reframing also resolves the center problem. If the early hot state was everywhere, then there is no special location where it went off, and no unique place to stand and point. The center dissolves, not by wordplay, but by symmetry. Every co-moving world line can be extended backward to higher density. Every observer can call themselves central in the same statistical sense, because the large-scale symmetries make center a property of the model, not of a location. The universe grants everyone the same cosmic privilege, which is to say, none at all. That is not a loophole, it is the content of homogeneity. The universe looks the same on large scales from any co-moving vantage, once you average over the local accidents of structure. The Milky Way is not special, and neither is any other galaxy when viewed from far enough away. If we could place cameras in distant galaxies and compare their sky maps, each would see the same broad story. Each would see a cosmic microwave background surrounding them, and each would infer expansion from redshifts, even if their local neighborhood looked different. The details would differ, but the statistical backbone would match. But this raises a new tension. If the early universe was everywhere hot and dense, why does it look so uniform across regions that seem causally disconnected, as though they coordinated their temperatures without communication? Uniformity is not automatic, because physics still needs time and contact to smooth things out. This is the horizon problem, and it is not a word game. It is a quantitative mismatch between causal contact and observed uniformity, and it emerges from drawing light cones on a space-time diagram. The diagram turns the puzzle into geometry, and geometry is hard to argue with. To see it, we imagine the universe as a space-time diagram with light cones. Signals travel at light speed, so only regions with overlapping past light cones can exchange energy and information, and only those regions can truly thermalize. The light cones are the universe's rulebook for communication. The CMB temperature is nearly the same across the sky. Regions separated by large angles on the last scattering surface were too far apart to exchange signals, if the early expansion was always decelerating in the simplest way. The puzzle is not that they are similar, but that they are so similar. Last scattering occurred when the universe cooled enough for electrons and protons to form neutral hydrogen. Photons then streamed freely, and those photons are what we detect as the CMB today, carrying a snapshot of conditions at that time. The moment is sometimes called recombination, though it was the first combination. Before that moment, the universe was opaque, like a bright fog. After that moment, it became transparent, and the photons began their long journey, stretched by expansion into microwave wavelengths. The screen can show this as a sudden clearing, a veil lifting from a glowing interior. In a simple decelerating expansion traced backward, their past light cones do not overlap enough. They should not have equilibrated to the same temperature, because there was not enough time for heat and information to spread. The causal horizon is too small to explain the observed uniformity. If they could not share heat, they should show larger differences, like patches of water that never mixed. Instead, the temperature variations are tiny, and the pattern is statistically subtle, with a nearly perfect blackbody spectrum underlying it. The blackbody shape is a signature of thermal equilibrium, and it is almost unnervingly clean. Yet they did, to 1 part in 100,000 after removing the dipole. The universe looks as if it had time to smooth itself, but the naive clock says no, and the geometry of causality makes the tension precise. The precision is what turns a curiosity into a problem. The dipole itself is a reminder that some anisotropy is mundane. It is largely our motion relative to the CMB rest frame, a Doppler imprint that disappears when we correct for it, leaving the deeper primordial pattern behind. Once removed, the remaining map is a fossil, not a reflection of our local speed. The remaining fluctuations are real, and they carry information. They are the seeds of galaxies and clusters, but they ride on top of an astonishingly uniform background temperature, implying a remarkable degree of early coordination. It is as though the universe agreed on a baseline, then allowed only tiny departures. The horizon problem is not solved by saying it was everywhere. Everywhere still contains regions that are space-like, separated at early times, meaning no signal travelling at or below light speed could connect them. Everywhere is a condition, but causality still draws boundaries, so the question sharpens. What mechanism set nearly identical initial conditions across a vast domain if causal processes were limited by light speed, and if the early universe did not have time to mix? The puzzle is not philosophical, it is written in the geometry of the past-like cone. A second tension sits beside it, quieter but equally sharp. The flatness problem is about why the universe's geometry is so close to spatially flat today, when curvature should have been dynamically unstable in simple histories. It is a question about balance, and about how easily balance is lost. In the Friedmann equations, curvature behaves like a term whose relative importance changes with time. In a decelerating universe, small deviations from flatness grow, so a near-flat universe today suggests an extraordinarily near-flat universe long ago. The equations make the sensitivity explicit, not merely suggestive. The key quantity is the density parameter, O, which compares the actual energy density to the critical density needed for flat geometry. Observations indicate O is very close to 1, meaning near flatness, and the error bars are small enough to make the puzzle unavoidable. The universe is not just kind of flat, it is flat to a striking degree. That means near flatness today implies extreme fine-tuning in the past. The early universe would have needed curvature tuned to an astonishing precision, because even tiny departures would have amplified over billions of years. The numbers are so severe that they demand either a mechanism or a remarkable coincidence. If O differed from 1 by even a tiny amount early on, the deviation would amplify over cosmic time in a decelerating expansion. The universe would either recollapse quickly or become curvature-dominated long before structures formed, leaving no time for galaxies. The fact that we see a long-lived structured cosmos is part of the evidence. This is not aesthetic discomfort, it is dynamical instability. Flatness is like balancing a pencil, unless something drives the system toward it, and the equations tell us that ordinary decelerating expansion does not provide that drive. The metaphor is imperfect, but the instability is mathematical. The metaphor is imperfect, but the instability is real. In many standard histories, flatness is not an attractor. Without a mechanism, it looks like an initial condition chosen with implausible accuracy, and the universe seems to begin already set up. The question becomes not only what happened, but why was it so special? So the Big Bang without a center solves one misconception and exposes deeper ones. It replaces where did it explode with why these initial conditions, and it forces us to ask what prepared the early cosmos. At this point, the central question returns with new force. If expansion is geometry changing, what set the geometry and its early smoothness, and why does the universe begin in such a special state? The mystery tightens, because the data do not merely allow the question, they provoke it. We also return to nothing, now with sharper definitions. Nothing can mean empty space inside spacetime, which still has geometry and vacuum fields, and still permits gravitational waves and quantum excitations. Empty is not featureless, it is simply unoccupied by ordinary matter. Even empty space in modern physics is structured. Quantum fields exist everywhere, and their lowest energy states still exhibit fluctuations that can be measured indirectly, from the Casimir effect to the statistical properties of primordial perturbations. The vacuum is not a void, it is a state with rules and restlessness. Nothing can mean a quantum vacuum, which is not absence but a state with fluctuations and possible energy density. Nothing can mean absence of spacetime itself, or even the notion of where evaporates. These are radically different meanings, and the narration has to keep them from sliding into each other. These meanings are easy to slide between in casual speech, and that slide creates confusion. A vacuum is not no laws, and it is not no arena, even when it looks visually blank on a screen. The blankness is a limitation of our eyes, not a statement about physics. The Big Bang model, as usually stated, does not begin from empty space. It begins from a hot, dense state with space-time already in play, and with physical processes that can be traced forward to today's relics. The model begins with something, and it is honest about that. If we ask, why is there space-time at all, we're asking a different question than why did matter spread out. That difference matters for honest narration, because one question is about initial conditions within a framework, and the other is about the framework's existence. The first is scientific in a direct way, the second may require a deeper theory. Still, cosmology does offer a candidate mechanism that addresses horizon and flatness together. It is a proposed early episode of accelerated expansion, inserted before the standard hot Big Bang evolution. It is not a decorative add-on, it is an attempt to explain why the initial conditions look prepared. Inflation is described as a brief period when the scale factor grew nearly exponentially. In that phase, a small causally connected patch could stretch to enormous size, making today's observable universe a magnified remnant of a once coherent region. The idea is simple to state, yet it rewires the causal diagram. Accelerated expansion means the expansion rate changes in a way that makes co-moving scales outrun the growth of the horizon. In plain terms, regions that were once in contact can be pulled far apart, while retaining their shared past and their nearly uniform conditions. The separation happens faster than light can traverse the growing distances, without violating relativity because it is the metric changing. That stretching can make distant regions share a common thermal past. It can also drive curvature toward near zero, making flatness less fine-tuned, because rapid expansion dilutes curvature's influence relative to the dominant energy component. What looked like an implausible balance becomes a natural outcome of a violent early smoothing. In the equations, rapid expansion dilutes any initial curvature term, the way a rapidly inflating balloon makes a small patch look flatter. The effect is not just geometric intuition, it is built into how curvature scales with AT, and how the Hubble radius evolves. The mathematics gives the analogy its teeth. Inflation also offers a way to seed structure. Quantum fluctuations stretched to cosmic scales can become the initial density perturbations seen in the CMB, providing a mechanism for the pattern of anisotropies we actually measure. The same process that smooths can also imprint, which is part of inflation's appeal. Those fluctuations start as microscopic variations in fields, governed by quantum uncertainty. As inflation stretches them, they become classical-looking variations in density, later amplified by gravity into the cosmic web of filaments, clusters, and voids. The universe's largest structures may trace back to quantum randomness, scaled up beyond imagination. The CMB power spectrum, its pattern of peaks and troughs across angular scales, acts like a fingerprint. It encodes both the primordial perturbations and the acoustic physics of the early plasma, and it strongly constrains inflationary scenarios, including their predicted spectral tilt. The data are not just consistent with inflation, they specify what inflation must look like. But inflation is not a free victory. It shifts the mystery to the physics that caused it, and to the conditions that started and ended it. Because accelerated expansion is not automatic in known particle physics. A mechanism must be real, not merely convenient. If inflation happened, what field drove it, and why did it have the right potential? Why did it begin, and why did it stop without leaving a mess, such as unwanted relics or excessive inhomogeneity? Each why is a scientific demand for dynamics, not a rhetorical flourish. Ending inflation requires a graceful exit, so that the universe reheats into the hot, radiation-filled state that standard Big Bang evolution assumes. That reheating must produce the right kinds of particles at the right densities without spoiling later successes like nucleosynthesis. The exit is where many models become constrained, because the universe must land on the track we know. And inflation reopens the word nothing in a more unsettling way. Some versions suggest inflation can start from a vacuum-like state, or spawn many regions, so the beginning becomes less like a single event and more like a process. The story becomes less like a spark and more like a phase transition. Then expansion into nothing becomes creation of space from a vacuum state, which is not intuitive nothingness. It is a physical state with laws, fields, and energy, and it can act as a source of gravity. The vacuum becomes an actor, not an absence. A vacuum-like state can still have energy, and that energy can gravitate. In inflationary language, it is the vacuum energy that drives accelerated expansion, turning emptiness into an active source of geometry, and making the word nothing feel almost misleading. The most powerful engine in the early universe may look at first glance like blankness. So we end the chapter with a controlled cliff edge. The Big Bang is not an explosion from a center, it is an early state of the whole universe, described by a changing scale factor and tested by relic light. The singularity is not a literal point, it is a breakdown of classical prediction. The Planck era marks where quantum gravity must take over, and where our smooth space-time picture becomes a provisional approximation. The horizon and flatness problems tell us the simple picture is incomplete. A mysterious growth spurt called inflation promises answers and deepens the question of nothing because it asks what kind of vacuum can make space grow. The universe does not expand into an outside. It expands by changing the geometry that defines distance. And the earliest moments test what geometry even means when the usual concepts of time and causality begin to wobble. In the darkness between equations and images, a final question hangs in the air. If everywhere can be the answer, what kind of reality makes that possible? The universe looks too smooth and too flat. Those are not compliments, and they are not aesthetic judgments, because in cosmology they function like fingerprints left at a crime scene. They are physical clues that point backward into the first fraction of a second when the rules we test today were being written into the geometry itself. On screen, the cosmic microwave background looks like a soft mottled shell around us, an ancient afterglow wrapped around the sky, almost perfectly uniform in temperature. The variations are tiny, measured in microkelvin, and yet the map is rich with structure if you know how to read it. The geometry inferred from that shell looks almost Euclidean, as if the cosmos refuses to curve in any measurable way across the largest distances we can survey. Smoothness and flatness sound simple, yet in cosmology, they are suspiciously specific outcomes, because generic beginnings tend to be messy. We already learned that expansion is geometry changing, not matter flying into an outside. Distances grow because the metric evolves, and that evolution is governed by general relativity, a theory that ties the shape of spacetime to the energy and momentum it contains. Now we ask why the geometry began so coordinated, and why it stayed that way long enough to become the stage for galaxies, stars, and the chemistry of life. We ask why distant regions share almost the same temperature, despite limited causal contact in the simplest early histories. We ask why the universe is so close to the boundary between open and closed, as if it were balanced on a knife edge for billions of years. We ask these questions because the data forces them, not because the mind enjoys puzzles, and the answers must respect the same equations that otherwise work so well. Inflation in one sentence. A brief early era of accelerated expansion stretched a tiny, connected patch into the vast region we now observe. That single sentence is a proposal, not a victory, because it is placed before the hot Big Bang track we can test in detail. It must land back on that track cleanly, and it must do so without erasing the later successes of standard cosmology, from light element abundances to the CMB's blackbody spectrum. Inflation aims to solve horizon and flatness together, while also explaining the seeds of structure, so it carries an unusually heavy burden for a single idea. Historically, this idea emerged when cosmologists confronted a mismatch between elegant equations and awkward initial conditions. In the late 1970s, the standard Big Bang picture worked beautifully for nucleosynthesis, and for the very existence of the CMB, which had been discovered in the 1960s and measured with growing precision. Yet the same framework seemed to require the early universe to be tuned with extraordinary precision, as if the cosmos began already arranged with the right settings dialed in. Inflation was the attempt to turn that arrangement into a dynamical outcome, rather than a mysterious starting gift. Instead of assuming special initial conditions, it asked whether early physics could drive the universe toward them, the way friction drives a swinging pendulum toward rest. If it works, smoothness and flatness become attractors, states the universe naturally approaches, even if it did not begin exactly there. Start with the horizon problem in operational terms, because it is not a philosophical complaint but a calculation. The cosmic microwave background is nearly uniform across the sky, to one part in about 100,000, and that uniformity extends across regions that appear widely separated. In the simplest decelerating early expansion, widely separated regions of the CMB never shared signals, heat, or particle interactions, because there was not enough time for light to cross between them. The horizon here is not a wall, and it is not the edge of space. It is a causal boundary set by light travel time in an expanding geometry, and it defines which regions could have influenced each other through any physical process. When we look at opposite sides of the sky, we're comparing patches that, in a simple model, were never in contact, and yet they look as if they agreed on a common temperature. Visualize the early universe as a hot plasma where photons, electrons, and baryons scatter constantly, like a dense fog of charged particles and light. Photons do not stream freely then, because electrons keep grabbing and re-emitting them, so the whole system behaves like a coupled fluid. In ordinary thermodynamics, a system becomes uniform because parts of it exchange energy and equilibrate, and the CMB's uniformity looks like the signature of just such equilibration. The horizon problem says that, without inflation, the CMB looks as if equilibration happened across a region too large to have equilibrated. Inflation changes the causal diagram without breaking relativity, and that clause matters because it is easy to misunderstand what is being claimed. It does not require faster-than-light motion through space, and it does not let information outrun light locally, where physics is measured. It says those regions were once close enough to equilibrate, then were pulled apart by rapid expansion, so their later separation is a geometric effect. The uniformity becomes inherited, not coordinated at distance. A small patch can be causally connected, settle to a common temperature, and then be stretched so dramatically that it later appears as many disconnected regions on the sky. The CMB's sameness becomes a fossil of an earlier closeness, preserved because the expansion carried it outward faster than new differences could form. On a spacetime diagram, inflation tilts the story in a way that is initially counterintuitive. World lines remain local and causal, yet the co-moving scale that becomes our observable universe is pushed outside the Hubble radius during the accelerated phase. The diagram looks like a trick, but the trick is geometry, an evolving metric that changes what within reach means. Then the flatness problem becomes a dynamical statement, rather than a philosophical annoyance about why the universe happens to be this way. In standard decelerating histories, any small curvature grows in relative importance over time, because the curvature term dilutes more slowly than the dominant energy density. Near flatness today implies extreme fine-tuning in the early universe, the kind that makes physicists suspect a missing mechanism. To say it plainly, the density of the universe had to start astonishingly close to the critical value, an almost perfect balance between expansion and gravitational pull. If it began slightly above, it would have recollapsed quickly, and if it began slightly below, it would have emptied out too fast for galaxies to form. The fact that we see a universe still expanding and still near the boundary is the clue, and the clue points to an early process that drove the balance toward critical. Inflation makes flatness less fragile. Accelerated expansion drives the curvature term toward insignificance, because the scale factor grows so quickly that any initial curvature is stretched away, like wrinkles pulled taut. A small patch becomes flatter in the same mathematical sense that a huge sphere looks locally flat when you stand on it. The analogy is visual, but it is also quantitative, and the numbers are part of the persuasion. If you zoom in on a curved surface, the curvature becomes harder to detect, and triangles look more Euclidean, because the deviation from flat geometry shrinks with scale. Inflation is like an extreme zoom-in on spacetime itself, an expansion so rapid that curvature becomes nearly invisible within the patch we later inhabit. Now we need the engine. In general relativity, not only energy density but also pressure gravitates, and that is the hinge on which the whole idea swings. This is where intuition breaks, because everyday pressure is a force on walls, and we learn to treat it as something that pushes outward. In a relativistic fluid, pressure is a component of energy and momentum flow, and it enters the gravitational field equations on equal footing with density. Gravity in GR responds to how energy is distributed and how it moves, not just to how much mass sits in one place. In the Einstein equations, the source is not just stuff, but the stress-energy tensor, a compact bookkeeping device for density, pressure, and momentum flux. That tensor tells spacetime how to curve, and the curvature tells matter how to move, creating a feedback loop between content and geometry. When pressure is large and positive, it can help gravity pull inward rather than push outward, which is the opposite of the everyday picture. Introduce the equation of state as a compact handle on this behavior, because it turns a complex fluid into one interpretable number. We compare pressure P to energy density R, often through the ratio PR, and that ratio determines how the energy density changes as the universe expands. Different cosmic components have different W values, and those values control how expansion accelerates or decelerates over time. Matter has negligible pressure compared to its energy density, so W is approximately 0, and its density falls as the volume grows. Radiation has positive pressure, with W near 1/3, and that pressure contributes to gravity even while it supports sound waves in the early plasma. A vacuum-like component has negative pressure, with W near -1, and that flips the sign of the effect in the acceleration equation. Inflation requires something close to vacuum-like behavior, at least for a short time. The energy density stays nearly constant while space expands rapidly, meaning it does not dilute the way matter or radiation does, and that persistence is what allows accelerated expansion to continue. The pressure is negative enough that the expansion accelerates, so the scale factor grows almost exponentially for many e-folds. Say the key condition without heavy math, but with the right physical meaning because the sign matters more than the symbols. In the Friedmann acceleration equation, acceleration occurs when r plus 3 times p becomes sufficiently negative, so pressure can dominate the outcome. Negative pressure can act like repulsive gravity, not by pushing outward into space, but by changing how the metric evolves and how geodesics separate. This is the first major reframing of nothing, and the language is misleading if you take it literally. Inflation is often described as driven by vacuum energy, and that phrase sounds like emptiness, like a blank stage. Yet in the equations it behaves like a powerful source, capable of dominating the cosmic budget and controlling the expansion rate. In quantum field theory, empty space is not the absence of fields, and that is one of the deepest shifts in modern physics. Fields are present everywhere, like invisible mediums with values at every point, and particles are excitations of those fields, the ripples we can detect. The vacuum is the lowest energy state of the fields, not a literal void, and lowest does not mean zero in any simple sense. Even in that ground state, fluctuations remain. Quantum uncertainty prevents a field and its rate of change from both being perfectly fixed, so the vacuum seethes with temporary variations constrained but unavoidable. These are not particles popping in and out as a cartoon, but real fluctuations in field amplitudes, encoded in measurable correlations. So vacuum energy is not a poetic label. It is a statement that the vacuum state can carry energy density, and that energy density can gravitate. Because gravity couples to energy in all its forms. If it is approximately constant, it behaves like a cosmological constant for a time, producing the negative pressure needed for accelerated expansion. This links inflation to the documentary's central question with a sharper edge. Expansion does not require an external room, because the room is the metric itself, and the metric is what defines distance in the first place. If a vacuum-like state changes the geometry, space can stretch from within, with no outside and no edge, and the concept of into becomes a category mistake. But inflation is not just smoothing, and it is not just flattening, because a perfectly uniform universe would remain empty of structure. It must also imprint the tiny irregularities we later measure, because those irregularities are the starting points for gravitational growth. The universe is almost uniform, yet not perfectly uniform, and that imperfection is the origin of everything structured, from clusters of galaxies down to the environments where stars form. Quantum fluctuations provide the raw randomness, but inflation provides the amplifier that makes them cosmically relevant. During inflation, microscopic fluctuations in the inflating field and in the metric arise from quantum uncertainty, as they must in any quantum system. Inflation then stretches those fluctuations to astronomical scales, turning subatomic jitter into cosmic architecture, and it does so in a way that preserves a distinctive statistical pattern. The crucial step is horizon crossing, and the phrase is easy to mishear, because it sounds like something physically travels past a boundary. A fluctuation begins smaller than the Hubble radius, where causal microphysics can act, and where waves can oscillate like ordinary vibrations. Rapid expansion pushes its wavelength beyond the Hubble radius, where it effectively freezes as a classical-looking perturbation, because regions of the wave can no longer communicate. Freeze does not mean it stops existing, and it does not mean time halts for the universe. It means the mode's amplitude becomes nearly constant because causal forces cannot act across the full wavelength, so the oscillation cannot complete its cycle. The perturbation becomes a stored pattern in the curvature of space-time, like a note held because the instrument can no longer change it. Later, after inflation ends, the Hubble radius grows again during the standard hot Big Bang evolution, and the causal horizon catches up. Those frozen perturbations re-enter, becoming density variations that gravity can amplify, and the same pattern becomes the blueprint for the cosmic web. What began as a quantum variance becomes, through expansion and later gravitational instability, the map of where matter prefers to gather. On screen, we can imagine a grid painted on space, stretching faster than any signal can cross it, while the camera pulls back in a smooth, relentless zoom. Tiny ripples in the grid are pulled wide like ink flecks smeared across an inflating balloon, except there is no balloon in an external room and no center you can point to. The stretching is intrinsic, and the ripples become the seeds, subtle at first and then decisive. Connect this directly to the CMB anisotropies because the sky is our data record. The temperature speckles in the CMB trace primordial curvature and density perturbations, projected onto the last scattering surface where photons finally decoupled from matter. Inflation predicts they should be nearly scale invariant, with a slight tilt, and largely adiabatic, meaning the fluctuations are shared across components. Scale invariant means the fluctuations have almost the same strength on many length scales, so no single scale is privileged in the primordial pattern. The tilt is the subtle deviation from perfect scale invariance, and it encodes the slow evolution of the inflating state as it rolls. Adiabatic means different components fluctuate together, preserving overall composition locally, so a slightly denser region has proportionally more of everything. The measured spectrum is close to that, and the closeness is one reason inflation became central rather than peripheral. The spectral index is slightly less than 1, consistent with many slow-roll inflation models, and it is measured with impressive precision using satellites and ground-based experiments. That slight tilt is not a decorative detail. It is a quantitative handle on the shape of the inflaton potential, the energy landscape that controlled the expansion. Explain Gaussianity as a testable fingerprint, because statistics are sometimes more revealing than pictures. If the perturbations are nearly Gaussian, their statistics are mostly captured by the two-point correlation function, or equivalently the power spectrum, and higher-order correlations are small. Significant non-Gaussianity would indicate more complex dynamics, multiple fields, or non-standard initial states, so it functions like a lie detector for simple models. Gaussianity is also a statement about simplicity in the face of randomness. A Gaussian random field is what you expect when many small, independent contributions add up, and it makes the universe statistically predictable, even when individual outcomes are random. Inflation's quantum origin naturally leans toward this kind of distribution, although small deviations remain a target of intense searches. Inflation also predicts a specific phase relationship that shows up as a striking visual pattern, and this is where the CMB becomes almost musical. The perturbations set initial conditions for acoustic oscillations in the photon baryon plasma, like sound waves in a hot, dense fluid. The observed CMB peak structure matches coherent initial phases, supporting an inflation-like origin, rather than a scenario with random phase disturbances. Those peaks are not arbitrary bumps, and their spacing carries geometric information as well as dynamical history. They are the harmonics of a cosmic instrument, where gravity compresses and radiation pressure pushes back, creating oscillations that freeze at last scattering. The fact that the peaks line up as they do tells us the initial perturbations were coherent, not noise stitched together from disconnected regions. Now introduce the second kind of fluctuation, because inflation is not limited to density ripples. Inflation can generate tensor perturbations, which are primordial gravitational waves, ripples in spacetime itself that stretch and squeeze distances as they pass. They would leave a distinct imprint in CMB polarization, especially a B-mode pattern with a swirling geometry that cannot be made by density perturbations alone. Polarization is a subtle messenger, and it requires a specific visual to make sense. When CMB photons scatter off electrons, they pick up a preferred orientation if the radiation field has a quadrupole pattern, so polarization records the geometry of the light's last interactions. Scalar perturbations mainly generate E modes, while tensor modes can generate B modes, making polarization a kind of filter for early universe physics. This is where the mystery becomes empirical, because the signal is difficult but not metaphysical. We have strong constraints on tensor modes, but no definitive detection of primordial B modes, despite intense effort and careful accounting for foreground dust. The tensor-to-scalar ratio remains an open window into the inflation energy scale and the steepness of the potential, and each improved limit reshapes which models remain plausible. If tensor modes were detected at a significant level, it would imply inflation occurred at an enormous energy scale, near grand unification territory, where forces may have merged. If they remain undetected as limits tighten, the story shifts toward lower-scale inflation, or toward models where tensors are naturally suppressed by dynamics. Either outcome is informative because it tells us what the early universe was not, so inflation is both powerful and incomplete, and that tension is part of its fascination. It explains why the universe is smooth, why it is nearly flat, and why it has the right spectrum of primordial seeds. Yet it does not tell us which field did it, or why its potential had the required shape, or why the universe began in a state that allowed inflation to start. Name the inflaton carefully as a placeholder, because the word can mislead by sounding like a confirmed particle. Many models posit a scalar field whose potential energy dominates briefly, acting like an effective vacuum energy that drives accelerated expansion. The field slowly rolls down its potential, keeping the energy density nearly constant, then eventually ends inflation when the conditions for acceleration fail. Slow roll is a technical phrase with a simple meaning, and it is constrained by what we see in the sky. The field changes gradually enough that its potential energy outweighs its kinetic energy, maintaining negative pressure and a near-constant Hubble rate. This gentle motion also produces the slight spectral tilt we measure, linking microphysics to sky maps through a chain of cause and effect. That ending is not optional, and the universe gives us no room to hide from that requirement. The universe we observe is hot and filled with particles and radiation, and it has a thermal history we can test through relic abundances in the CMB spectrum. Inflation must transition into that hot state, or it would leave a cold, empty universe that never forms atoms, stars, or observers. This transition is reheating, and it is where the early smooth geometry meets the complexity of particle production. As inflation ends, the inflaton's energy must convert into ordinary particles and radiation, repopulating the universe with a hot plasma and restoring a thermal bath. The universe becomes thermal again, setting the initial conditions for the standard Big Bang evolution that follows, including nucleosynthesis and later recombination. Reheating is where the clean geometry meets messy particle physics, and the mess is not a flaw, but a physical necessity. It depends on couplings between the inflaton and other fields, and those couplings determine what particles are produced and how quickly energy is transferred. It must produce the right entropy, the right temperatures, and avoid unwanted relics that would overclose the universe or spoil nucleosynthesis. In some scenarios, reheating is not an instant switch, but a complex process with stages and instabilities. The inflaton can oscillate around the minimum of its potential, behaving like a coherent condensate that decays into other particles over time. Nonlinear effects can lead to preheating, where particle production happens explosively through resonances, briefly filling space with highly occupied modes before full thermalization. These details matter because they affect what comes next, even if we keep the focus on inflation's core role. The reheating temperature influences baryogenesis possibilities and the production of dark matter candidates, because it sets which reactions can occur in the early plasma. Inflation must solve early puzzles without breaking later successes, like nucleosynthesis and the CMB, so reheating is part of the contract. We can state the narrative constraint plainly, because the documentary's logic depends on it. Inflation must be a bridge, not a detour, and it must deliver a universe that looks like ours by the time the hot Big Bang begins. The elegance of the early stretch is judged by its ability to rejoin the tested thermal track, leaving behind signatures but not contradictions. Now return to the meaning of nothing with sharper edges. In everyday language, nothing means absence of stuff, a blank stage with no actors and no properties. In quantum field theory, empty space still has fields and fluctuations, and it may carry vacuum energy, so nothing becomes a state with structure. So when we say inflation can start from a vacuum-like state, we are not saying it starts from literal non-existence. We are saying it starts from a physical state with a stress energy content, described by laws and by a field configuration that can be stable or metastable. The vacuum is a kind of something, defined by the theory, and its properties are among the most consequential unknowns in physics. This matters for the central paradox, because it reframes what it would even mean to expand into anything. The universe does not expand into a pre-existing void, because there is no external container in the model, and there is no boundary where the expansion meets an outside. It expands by changing the metric, and the metric responds to stress energy, even when that stress energy belongs to a ground state that contains no particles. Inflation therefore reframes the question rather than closing it, and that is why it feels both satisfying and unsettling. If vacuum energy can drive expansion, then emptiness is not inert, An absence of particles does not mean absence of gravitational influence. The vacuum becomes an active participant in cosmic history, a driver rather than a background. At the same time, the word vacuum hides complexity, and the complexity is not optional. In quantum field theory, different vacua can exist, and a field can be trapped in a metastable state, like a ball resting in a shallow valley rather than the deepest one. Inflation often relies on such an effective vacuum-like state lasting long enough to do its work, then changing so reheating can occur. Now we move from mechanism to tests. Inflation is not accepted because it is dramatic, and it is not rejected because it is strange, because cosmology is not a contest of intuitions. It is judged by quantitative predictions that can be compared to data, with uncertainties treated as part of the story, and with multiple lines of evidence cross-checking each other. First test is the spectral tilt, because it is measured well, and it speaks directly to inflation's dynamics. A perfectly scale-invariant spectrum would have n is equal to 1, a special value that would suggest exact symmetry in the inflating phase. Observations find n slightly below 1, which fits many models but constrains their parameter space, ruling out overly simple potentials. That constraint is not merely academic, because it eliminates entire families of early universe histories. It rules out broad classes of potentials that would produce too much tilt, too little tilt, or the wrong scale dependence across the CMB's measured multipoles. The CMB becomes a laboratory for energies far beyond any accelerator, using the sky as the detector and time as the experimental run. Second test is tensor modes, because they would be a direct signature of spacetime's own quantum fluctuations. Detecting primordial gravitational waves would strongly support inflation and measure its energy scale, because the tensor amplitude is tied to the expansion rate during inflation. Not detecting them pushes models toward lower energy scales or different dynamics, and it also forces theorists to be more explicit about what they are assuming. Third test is non-Gaussianity, because it probes whether inflation was simple or orchestrated by multiple ingredients. Simple single-field, slow-roll models predict very small non-Gaussianity, essentially a near-perfect Gaussian random field with only tiny corrections. A significant detection would force a more complex inflationary sector or an alternative to inflation, and it would reshape how we interpret the CMB's statistics. Fourth test is isocurvature, which asks whether all components fluctuated together or whether some species had independent variations. Inflation typically predicts primarily adiabatic perturbations, though multi-field models can generate isocurvature components where different species fluctuate independently. Current data strongly limits isocurvature, narrowing viable scenarios and pushing many models towards simpler behavior. We can also mention running and features, because the power spectrum may not be a perfect power law across all scales. Some models predict a scale-dependent tilt called running, or sharp features from potential steps and brief transitions as the inflaton move through its landscape. Data so far favors smoothness, but the search continues with every new survey, because even a small feature could be a clue to microphysics. Tie this to the documentary's earlier humility, because the method matters as much as the result. Cosmology cannot rerun the universe, and it cannot isolate one parameter while holding everything else fixed, so it relies on relics and cross-consistency. Inflation's predictions are written into those relics, especially the CMB and large-scale structure, and the agreement is statistical rather than photographic. Large-scale structure adds another layer of testing, and it brings inflation seeds into the present day. The same primordial spectrum that shapes CMB anisotropies also shapes how matter clusters into filaments, voids, and halos over billions of years. When simulations start with inflation-like initial conditions, they reproduce the broad statistical properties of the observed cosmic web, including the distribution of galaxies and the imprint of baryon acoustic oscillations. Now connect to late-time acceleration without confusing them, because the parallel is tempting but the epochs are distinct. Inflation is an early accelerated expansion, while dark energy drives a late accelerated expansion, separated by billions of years of decelerating history dominated by radiation and then matter. Both involve negative pressure-like behavior, and both raise the question of vacuum energy, but they operate at radically different energy scales. This parallel deepens the stakes, because it suggests the vacuum is not a minor detail. If vacuum-like energy can dominate twice, then the vacuum is not a footnote to the story, and it may be central to cosmic history. We still do not know its microphysical origin, and we do not know why its effective value would change or appear in different forms across time. Here the narration can linger on a visual rhyme, because the universe sometimes repeats motifs. Early inflation is a violent, brief surge that smooths and seeds, while late acceleration is gentle and persistent, stretching the cosmic web apart over immense time. Two accelerations bracket the universe's long middle age, and both whisper the same word, vacuum, while meaning it in slightly different ways. The Hubble tension becomes part of this chapter's pressure, because it hints that early universe physics may not be fully settled. If early universe physics is slightly different, it can shift the sound horizon and change the inferred H0, the present expansion rate, when we interpret CMB patterns. Some proposed fixes invoke extra early energy components, echoing inflationary ideas without being inflation itself, and the debate reminds us how tightly connected the inference chain is. So inflation sits near the fault line between early and late cosmology, even when it is not the direct cause of the tension. It shapes the initial conditions used in CMB inference, and it influences how we translate angular patterns into distances and expansion histories. It also shares conceptual DNA with dark energy, even if the epochs and scales differ, which keeps the vacuum question in the foreground. Now escalate into the most unsettling extension. Some inflation models are eternal, meaning inflation ends in some regions but continues in others, driven by quantum fluctuations that keep parts of the field from rolling down everywhere. The overall space-time keeps inflating while local pockets reheat and evolve like hot Big Bang universes, so the end of inflation becomes a local event. In that picture, our observable universe is one bubble region where inflation ended, reheating occurred, and the familiar thermal history began. Other bubbles could have different low-energy physics, depending on how fields settle into different vacua, and the differences could be dramatic or subtle. The word universe becomes ambiguous, meaning our region, or the larger inflating background, and the ambiguity is not just semantic. Frame it as hypothesis, not established fact, because the evidence is indirect and the extrapolation is bold. Eternal inflation is motivated by certain potentials and by the mathematics of inflationary dynamics, where quantum fluctuations can compete with classical rolling. It is a plausible outcome in some models, but it is hard to test directly, because other bubbles may be forever beyond our horizon. Its conceptual consequence is still worth stating, because it changes what beginning might mean. If inflation is eternal, there may be no single global end and no single reheating event, only many local endings scattered through an ever-expanding background. The hot Big Bang becomes a local beginning inside a larger inflating space-time, and our origin story becomes one chapter in a much bigger book. This returns to the opening hook in a new register, and the visuals can shift from maps to horizons. Imagine standing at the edge of everything, then realizing there is no edge, only horizons that limit what you can see, and those horizons are dynamic. Eternal inflation adds that there may not even be a single everything, only many regions with their own causal boundaries, each mistaking its horizon for a wall. It also sharpens the meaning of nothing again, because the inflating background can look empty in the particle sense. The background inflating space can be nearly empty of particles, yet full of vacuum-like energy, and that energy can generate new regions through dynamics. Emptiness becomes a generator rather than a void, and that is a profound shift in what we mean by nothing happening. But we keep the discipline of the documentary because speculation must be labelled and separated from measurement. We separate what inflation explains well from what remains uncertain, and we separate measured signatures from speculative extrapolations. Mystery is not a license to blur categories, even when the story is tempting. What inflation explains well is the pattern of initial conditions, and the explanation is unified rather than piecemeal. It offers a mechanism for smoothness and near flatness, and it offers a mechanism for the origin of perturbations with the right statistics and coherence. It turns several cosmic coincidences into outcomes of a single early phase, and that economy is part of its appeal. What remains uncertain is the engine, and the uncertainty is not a small footnote. We do not know the inflaton's identity, its potential, or its embedding in particle physics, and we do not know whether inflation was a single event or part of a larger eternal process. The mechanism is plausible, but the microphysics is still under negotiation, and different models can mimic the same broad predictions. We also do not know what vacuum energy truly is, and this ignorance is unusually sharp. Quantum field theory predicts vacuum contributions that seem wildly larger than the observed dark energy, a mismatch sometimes called the vacuum catastrophe. Inflation makes it harder to ignore because it relies on vacuum-like behavior to shape the universe, so the vacuum cannot be treated as a mere mathematical baseline. So the chapter ends with a controlled widening of the mystery, rather than a tidy conclusion. Inflation makes the universe's early order less miraculous, but it makes the vacuum more powerful and more puzzling. It replaces one kind of nothing with another kind of something, and it asks us to accept that empty is a physical state with consequences. The central question does not vanish, and the narration can let it hang in the air. How can the universe expand with no external space? And why should geometry respond so dramatically to a field's ground state? Inflation answers by doubling down on geometry, where expansion is the metric changing, driven by stress energy that can belong to fields even in their lowest energy configuration. The deeper question becomes why the vacuum has the properties it has, and why those properties are so effective at shaping cosmic history. Why it can drive a great stretch in the beginning and a gentler acceleration now, without tearing the later universe apart. Why quantum fluctuations become the seeds of galaxies, and why the laws allow that translation from randomness to structure, rather than washing it all away. As we look at the CMB's faint speckles, we are looking at amplified quantum uncertainty, frozen into a sky map and carried to us by ancient photons. As we map galaxies and voids, we are tracing the grown-up versions of those same primordial wrinkles, sculpted by gravity over billions of years. The universe is smooth enough to be describable, yet rough enough to be interesting, and that balance may be the most revealing clue of all. Next, we follow the consequences into what we can observe and what we cannot. Because horizons are not just distances but limits on explanation. We ask how horizons carve reality into accessible and inaccessible regions, and how that carving shapes what counts as an explanation in cosmology. We ask whether our cosmic patch is typical, or just one outcome among many, and what typical could even mean. The universe does not expand into nothing. It expands by changing the geometry that defines distance, time, and causal reach, and that change can be driven by energy forms that do not look like matter at all. Inflation suggests that even nothing in modern physics is not empty enough to stay quiet, because the vacuum itself can stretch the cosmos, and in doing so, it can leave a pattern we still see today. We return to the central paradox with inflation behind us and geometry in hand. We have a language for expansion now, and it is not the language of objects swelling into a surrounding void. If expansion is the metric changing, does it still require an outside, some larger arena that receives what grows? The hook survives because language keeps smuggling in containers and walls. We picture a growing object, we imagine its surface pushing outward, and we quietly assume a surrounding emptiness must already be waiting. Even the word space sounds like a room, and universe sounds like a thing inside it. General relativity offers a different claim, and it is stranger in a precise way. Distance is defined internally by space-time geometry, not by embedding the cosmos in a larger room. So we ask the question in a sharper form, with fewer metaphors and more operational meaning. Is the universe finite or infinite? And what would either option mean in measurements we could actually perform? The answer decides whether edges are physical features or mental artifacts produced by how brains visualize extension. Start with a boundary, because boundaries feel like common sense. A boundary is a place where you can stand, turn around, and point outward as if outside were a direction. In everyday life, boundaries are surfaces where material ends, like a coastline or a wall. In cosmology, a boundary would be a physical edge of space itself, not just a limit of observation. That distinction matters because the universe already has observational limits. We cannot see beyond a certain distance because light has had only so much time to travel. Yet those limits are not edges in the geometric sense, and they do not imply a cliff where space stops. A true boundary would be a place where geometry ends, where the rules for distance and direction break. The standard FLRW models do not require a boundary. They describe spatial slices, three-dimensional snapshots of space at a cosmic time that can be finite without having an edge. That phrase sounds like a trick until you separate geometry from embedding, and until you stop assuming every finite thing must sit inside something larger. A two-dimensional analogy carries the key idea without importing an outside. On a sphere's surface, you can travel forever without meeting an edge, and you never need to step off the surface to define distances. The surface area is finite, yet no point is a boundary, and no direction is outward along the surface. To make the visual concrete, imagine a tiny explorer walking with a ruler and a compass. Every step is measured along the surface. Every triangle is drawn on that curved skin. The explorer can map the world, compute angles, and detect curvature, all without ever referring to a third dimension. The outside exists for us, but it is irrelevant to the geometry the explorer can measure. Translate that to 3 dimensions with care, because the analogy is conceptual rather than literal. A 3-sphere is the 3-dimensional analogue of a sphere's surface, and it is a legitimate spatial geometry in general relativity. It is a finite volume space with positive curvature and no boundary, meaning there is no edge you can reach by travelling in any direction. In a 3-sphere, straight paths eventually return, like great circles on Earth. The technical term is geodesic, the path that locally maximizes proper time for free-falling observers and locally minimizes distance on a spatial slice. If you follow a geodesic far enough in a closed geometry, you do not fall off. You come back, not because of a wall, but because the space itself closes. There is no privileged center inside the space itself. The center exists only if you embed the 3-sphere in a higher dimension, like imagining the surface of Earth sitting in ordinary space. That embedding can be drawn on a chalkboard, and it can help intuition, but it is not required by the physics. The intrinsic geometry contains all measurable distances and angles, and that is what general relativity treats as real. This is where the category mistake hides. Asking what the 3-sphere expands into repeats the error of treating geometry like a balloon in a room. The balloon picture can be useful if you remember what it is doing. It is illustrating changing distances along the surface, not motion into an external volume. The outside in the picture is a crutch, not a prediction. Finite without boundary is not limited to the 3-sphere, and that is a key deepening of the idea. Flat space can also be finite if it wraps around, because topology can make a space compact even when curvature is 0. A 3 torus is locally Euclidean yet globally compact, which means small neighborhoods look like ordinary flat space, while the global identification makes paths loop. In a 3 torus, traveling far enough in one direction returns you from the opposite side. The return is not through a portal you can point to, and it is not a seam you can touch. It is a global identification of points, like the classic video game world where leaving one side of the screen brings you back on the other. Locally, rulers and triangles behave as in ordinary flat space, and that local familiarity is exactly why such a universe could hide. Hyperbolic spaces add another family of possibilities, and they complicate the simple curvature equals fate story. Negative curvature tends to produce infinite spaces when you keep the simplest topology, because volumes grow rapidly with radius. Yet some hyperbolic topologies can still be compact, meaning you can have negative curvature and still have a finite total volume. Curvature and finiteness are related, but they are not identical. This is the first tension beat, and it is a subtle one. Our measurements say space is close to flat, but that does not settle finiteness. Near-flat curvature could describe an infinite space, or a huge finite space whose wraparound scale exceeds our horizon. The universe can be finite and still look endless from any practical vantage. Explain why curvature is hard to measure directly. Because flatness is not something you can eyeball. We infer it by comparing observed angles and distances to model predictions, and by asking whether triangles add to 180 degrees in the large. In curved spaces, the relationship between distance and angle changes, and so does the way standard rulers project onto the sky. The cosmic microwave background provides one of those rulers, and it is almost absurdly ancient. Before atoms formed, the universe was a hot plasma where photons scattered constantly off free electrons. When it cooled enough for electrons to bind to nuclei, light decoupled and began streaming freely, carrying an image of that last scattering surface. Embedded in that image is a characteristic scale, the sound horizon, set by acoustic waves in the early plasma. The CMB acoustic peak scale acts like a standard ruler projected onto the sky. In a positively curved universe, that ruler appears larger because geodesics converge and angles are effectively magnified. In a negatively curved universe, it appears smaller because geodesics diverge and the same physical scale subtends a smaller angle. By measuring the angular size of that feature, we constrain curvature. Planck and other data constrain spatial curvature tightly. The result is consistent with k equals 0 within small error bars, and the statistical language matters here. Consistent with flat means the best fit curvature is near 0, and the uncertainties overlap 0. It does not mean we have proven the universe is infinite, because topology can hide behind flatness. A finite universe can look flat if its curvature radius is large, and large here means enormous compared to the observable patch. A compact flat topology can look infinite if its fundamental domain is larger than what we can see, because wraparound effects would lie beyond our horizon. Observational humility is part of the story, and it is not a weakness. It is a recognition of what light can and cannot tell us. Now define what infinite would mean in practice, because infinity is not an image we can look at. It means spatial slices extend without bound and do not wrap around, so there is no global identification that returns you. It does not mean we can observe infinity, because observation is limited by light travel time and by the finite age of the hot early phase. An infinite universe also does not guarantee infinite matter in any useful sense. It implies infinite volume in the model, but physical conclusions depend on assumptions about homogeneity extending forever. The cosmological principle that the universe is statistically homogeneous and isotropic on large scales works remarkably well within what we observe. Extending it to infinity is a stronger extrapolation, and it is a philosophical move disguised as a technical one. So we pivot to topology as an observational question. If space is compact, light can take multiple paths, because geodesics can wrap around. The same region could be seen in different directions, like a hall of mirrors without walls. The mirrors are not objects in space, but identifications of space itself. The most famous target is the cosmic microwave background, because it is a nearly perfect backlight. A compact topology could produce matching circles in the CMB sky, where the same last scattering patch appears twice. The prediction is specific. Pairs of circles with correlated temperature fluctuations, aligned in a way that encodes the topology's size and orientation. This is a clean signature in principle and brutal in practice. Foreground emission contaminates the microwave sky from our own galaxy's dust and synchrotron radiation. Instrument noise and beam effects blur small-scale features, while cosmic variance limits what we can infer from the larger scales, because we have only one sky. Masking regions to remove foregrounds also removes data, and topology signals can hide in those missing pieces. Topology signals also depend on the size and shape of the fundamental domain. If the wraparound scale is larger than the last scattering surface, the circles do not appear because the light has not had time to complete a loop. If it is only slightly smaller, the correlations can be weak, and they can be confused with chance alignments in a random field. Even the thickness of the last scattering surface matters, because it smears the pattern and softens the edges of the circles. Current searches have not found convincing matched circles, and that absence is informative. It sets lower bounds on the size of many compact models, effectively saying that if space wraps, it wraps on scales at least comparable to the observable universe. The bounds are strong but not absolute, and loopholes remain for certain shapes, orientations, and topologies that produce subtler signatures. Large-scale structure offers another route, because galaxies trace the underlying distribution of matter. A compact topology could repeat patterns in galaxy distributions, producing multiple images of the same structures at different redshifts. Yet the universe is not a static lattice, and that complicates the search. Nonlinear evolution distorts the pattern. Galaxy bias changes how light traces mass, and survey incompleteness leaves gaps that can mimic or erase repetition. Even so, the logic is powerful. If we ever saw unmistakable repetition, it would not merely suggest finiteness. It would tell us the universe's global shape, the way a map of Earth reveals that the world wraps. The fact that we have not seen it yet does not mean it is not there. It means the universe may be larger than our reach, or shaped in a way that hides its seams. So we sit with the result, and we let it remain unresolved in the right way. The universe could be infinite, or it could be finite and unbounded, with a scale beyond our view. Either way, the existence of an exterior is not implied, because neither finiteness nor infinity requires a surrounding container. The outside is a picture we import, not a feature demanded by the equations. This is the transition back to the central paradox, and now the words can be cleaner. Expansion does not demand an outside because expansion is not motion into a container. It is the time evolution of the metric that defines distance between co-moving world lines, observers who ride the Hubble flow and see the universe as homogeneous around them. To ground that, imagine a grid of galaxies with no forces between them except gravity on large scales. In the flow description, those galaxies are at rest in co-moving coordinates, and the scale factor AT changes with time. Proper distances grow because the metric changes, not because the galaxies are firing rockets through space. The geometry is doing the stretching, and the stretching is what we call expansion. Now we raise the stakes with the expansion we live in today. The universe is not just expanding, and it is not merely coasting from an explosive beginning. It is accelerating, and acceleration reshapes what reachable means. It changes not only what we can see now, but what we can ever see. The first strong evidence came from Type Ia supernovae, which act as standardized candles after calibration. Teams in the late 1990s found distant explosions dimmer than expected in a decelerating universe, implying they were farther away than the old models predicted. The inference was that expansion has sped up over the last several billion years, and that result has been cross-checked with baryon acoustic oscillations and CMB-based distance measurements. In the Friedmann equations, acceleration depends on energy density and pressure, and the pressure term is not a footnote. In general relativity, pressure gravitates, meaning it contributes to the curvature of spacetime just as energy density does. A component with sufficiently negative pressure drives accelerated expansion, because it makes the right-hand side of the acceleration equation negative in the right way. This is where dark energy enters as a name for the missing term. The simplest candidate is a cosmological constant, L, originally introduced by Einstein and later reinterpreted. In modern language, it behaves like constant energy density of the vacuum, uniform in space and constant in time. Its pressure is negative and equal in magnitude to its energy density, which is a peculiar equation of state that makes it act repulsively on cosmic scales. Introduce the equation of state parameter in accessible terms because it compresses a lot into one symbol. We write W as pressure divided by energy density, and we use it to summarize how a component responds to expansion. Matter has W near zero because its pressure is negligible compared to its energy density. Radiation has W near 1/3 because photons carry pressure as they stream. L has W equal to -1, which is the special value that produces constant energy density. If W equals -1, the energy density does not dilute as space expands. That constancy makes L dominate at late times as matter thins out, even if L was small in the early universe. The expansion then approaches exponential growth, where the scale factor grows roughly like e to the h. In that regime, the universe's large-scale behavior becomes increasingly simple and increasingly isolating. But L is not the only possibility, and the alternatives keep the mystery alive. Dark energy could be a slowly evolving field, often called quintessence, whose energy density changes over time. In that case, W can differ from -1 and can change with time, and the history of acceleration becomes a clue to the underlying physics. The challenge is that many different models can mimic W close to -1 over the limited time window we can probe. Observations currently favour W very close to -1, and the error bars are tightening. The uncertainties still allow small deviations and mild evolution, and each decimal place matters because it distinguishes a constant vacuum term from a dynamical component. A tiny drift in W with Redshift would be a major discovery, because it would mean the acceleration is not simply a fixed property of space-time. This is where the vacuum problem echoes from earlier chapters, and the echo is sharp. Quantum field theory suggests vacuum contributions that are wildly larger than the observed L, depending on how one estimates the zero-point energy. The mismatch is not a minor discrepancy that can be waved away by calibration. It is a gulf between theory and observation, and it remains one of physics' most persistent unsolved problems. We also flag the alternative, because it is part of the same operational landscape. Accelerated expansion could reflect modified gravity on large scales, meaning the left side of Einstein's equations changes rather than adding a new energy component on the right. Many such theories are constrained by tests in the solar system and by structure formation, yet the possibility remains as a reminder. When we say dark energy, we may be naming our ignorance rather than a substance. But the documentary keeps the focus on consequences we can describe without committing to a cause. Whatever drives acceleration, it produces horizons that are not just about the past. It creates a limit on the future, and that limit is geometric, not technological. Even perfect instruments cannot see past a horizon defined by space-time itself. Define the particle horizon briefly to keep terms clean, because the word horizon can mean different things. The particle horizon is the maximum distance from which light has reached us since the hot early phase. It marks the size of the observable universe today, given the finite age of the cosmos and the finite speed of light. Now define the event horizon, which is the new character in this chapter. The event horizon is the maximum distance from which light emitted now can ever reach us in the future. In an accelerating universe, that distance can be finite, which means there are regions that exist and evolve but can never send us new information after a certain time. The horizon is not a place in space so much as a boundary in space-time. This is where the phrase, receding faster than light appears, and it must be handled carefully because it triggers the wrong intuition. In expanding space, recession speed is the rate of change of proper distance, and it can exceed c without any object locally moving through space faster than light. The metric can make distances grow so quickly that the separation increases superluminally, even though each galaxy is locally at rest in its own co-moving frame. Relativity is safe because special relativity limits local speeds measured in local inertial frames, not global recession defined across curved space-time. Superluminal recession is a global geometric effect, not a local violation. No signal outruns light in its immediate neighborhood, and no observer sees nearby physics break. The confusion comes from treating speed as if it had only one meaning in all coordinate systems. The event horizon is not a material wall, and it is not a shock front sweeping outward. It is a boundary in space-time that separates events that can influence us from events that never can. It is defined by future light cones, not by the present snapshot, which is why it feels counterintuitive. You cannot point to it in the sky with a finger, yet it shapes what the universe can ever tell us. In an L-dominated future, more and more co-moving regions cross this horizon. Light they emit after crossing will never reach us, even if it is emitted in our direction, and even if we wait forever. The universe does not lose those regions physically, but it loses causal contact with them. They become part of reality that is real in the model and real in principle, yet permanently silent to us. This creates the chapter's eerie consequence, and it is worth lingering on the imagery. The universe can keep expanding while our accessible universe effectively shrinks in co-moving terms. The map of what can ever be observed becomes smaller relative to the whole, like a spotlight narrowing while the stage grows. Expansion makes more space, yet acceleration makes less of it relevant to us. Now connect this to galaxies and the night sky, because horizons are not only equations. Today we see galaxies out to high redshift, and we see the CMB as a relic surface that wraps the sky. Each faint smudge is a time capsule, because its light left when the universe was younger and denser. The sky is a layered archive, and acceleration threatens to close the archive. Some galaxies are already beyond the event horizon, in the sense relevant to future signals. We can see their past light, emitted long ago, because it began its journey before the horizon boundary became decisive. But we will never receive their later light, emitted after they cross the horizon. The distinction between seeing and continuing to see becomes crucial, and it is a distinction our intuition rarely practices. As acceleration continues, more galaxies will slip beyond reach. Their photons will be stretched to longer wavelengths and lower energies, and the stretching is not just a color shift. It is a dilution of information, because each photon carries less energy and arrives less frequently. Eventually they become undetectable against backgrounds and instrument limits, not because they vanish, but because the universe redshifts them into silence. Local gravitationally bound structures resist expansion internally, and that is another important clarification. The Milky Way does not expand, the solar system does not expand, and atoms do not expand with the Hubble flow. Gravity, electromagnetic forces, and binding energy dominate on small scales, holding structures together against the gentle pull of cosmic expansion. The Milky Way and Andromeda will merge, and the local group remains bound as a long-lived island. But beyond that island, the cosmic web thins from our perspective. Filaments and clusters that are not gravitationally bound to us recede, and the acceleration makes their recession increasingly irreversible. Over vast times, the visible universe becomes dominated by what is nearby and bound, while everything else fades into an unreachable beyond. The large-scale universe does not end, yet it ends for us observationally. In the far future, the sky becomes quieter in a literal, measurable sense. External galaxies disappear from view, leaving only local remnants and the dim afterglow of long-lived stars. The CMB itself redshifts to wavelengths so long that it becomes effectively unmeasurable, swamped by plasma effects and by the practical limits of detectors. The relic radiation that once shouted, "hot beginning," becomes a whisper below any plausible noise floor. This is not just poetic darkness, and it is not merely a melancholy thought experiment. It is a statement about information loss due to horizon structure, a consequence of the way light cones carve space-time. Future observers could have less evidence for the Big Bang than we have now, even if they are smarter and more technologically advanced. The universe can hide its own history by stretching the evidence away. They might not detect the Hubble flow beyond their local group, because there would be no external galaxies visible to map a redshift distance relation. They might not detect the CMB as a thermal relic, because it would be too cold and too diluted to measure. They could infer a static island universe and miss the larger story, not through error, but through lack of accessible data. That possibility reframes cosmology as a time-limited enterprise. Some facts are knowable only in a window when relics are still visible, when the sky still contains distant beacons and ancient backgrounds. The universe itself sets an expiration date on certain measurements, and that is a profound constraint on what science of the whole can mean. We are not only observers in space, we are observers at a particular cosmic time. Now bring back the Hubble tension as a pressure point, not a detour, because it illustrates how inference depends on global assumptions. We measure H0 locally with Cepheids and supernovae, building a distance ladder outward from nearby calibrators. We infer it from the CMB by fitting a model to early universe physics and projecting forward. The two answers disagree at a level that has resisted easy fixes, and the disagreement forces us to ask what we're assuming. If the tension is real, it could hint at new physics that changes early expansion or the sound horizon, subtly altering the ruler we use. It could also reflect hidden systematics in one or both measurement chains, from calibration drift to selection effects. Either way, it reminds us that cosmology is an inference engine built on limited data. The universe is not handed to us whole, and our conclusions are only as solid as the scaffolding. This chapter uses that reminder to sharpen the climax. If topology, curvature, and dark energy all sit partly beyond direct reach, then the universe becomes a layered concept rather than a single object. There is the observable universe bounded by the particle horizon. There is the potentially larger connected region, which could wrap or extend far beyond what we see. And there is the possibly infinite whole, which may include regions forever causally disconnected. So what does everything mean operationally, in a universe with horizons and uncertain global shape? It can mean everything that can ever affect us, bounded by the event horizon and defined by causal contact. It can mean everything that exists on a spatial slice, which may be finite or infinite depending on topology and curvature. It can mean the totality across all regions, even those forever causally disconnected from us. These meanings are not interchangeable, and the documentary leans into that discomfort. If more of reality becomes unreachable over time, then everything is not a stable target for measurement. It becomes a word that outruns the instruments, and a concept that drifts away from operational definition. We can say, the universe, yet we must ask which universe we mean. Now return to the original phrase that started the paradox, because it is still doing psychological work. Expanding into nothing assumes an exterior that receives the expansion, like a vacuum outside a balloon. But in general relativity there may be no exterior, because space can be finite without boundary or infinite without edge. And in accelerated expansion, there may not even be future access to much of the interior, because horizons cut causal ties. So the paradox flips, and the flip is the point. The question is not what space expands into, as if space were a substance with a frontier. The question is why space-time has the geometry and stress energy content that makes distances grow, and why the growth accelerates now. The mystery moves from imagined walls to the actual terms in the equations. We can state the key insight cleanly, and it is both simple and unsettling. A finite universe can have no edge, and an infinite universe still has no boundary you can reach. In both cases, outside, is not a required category, and the demand for it is a habit of visualization. Geometry is not obliged to satisfy the metaphors of everyday objects. We can also state the new unease, because it is the emotional peak of the science. Acceleration creates an event horizon that turns much of the universe into a permanent beyond. The universe can be real, and yet operationally inaccessible, which means reality can exceed evidence in a structured, predictable way. The limit is not ignorance we can fix. It is a boundary written into space-time. This is the tension peak for this chapter. If cosmology is built from light that reaches us, then a horizon is not just a distance. It is a limit on what counts as evidence, and therefore a limit on what counts as a test. The universe can be larger than our models can ever confirm, and quieter than our instruments can ever overcome. So we end by tightening the central question rather than relaxing it. If the universe does not expand into an outside, and if horizons erase access to most of what exists, what does it mean to talk about the universe as a whole? Are we describing a physical totality, or a causally connected domain, or a mathematical extension of a principle that worked so far? The next chapter will not add an exterior, because that would be a retreat to the old picture. It will ask what nothing could mean when space-time itself is the thing that changes, and when vacuum is not truly empty. It will ask why geometry has the properties it has, when intuition keeps demanding edges that physics refuses to provide. We began with an edge in the mind, a cliff at the end of everything, and a dark beyond that begged for a name. We end by admitting the edge was never part of the model, only part of the picture we carried. The central question was always linguistic as much as physical, because words smuggle in geometry. If the universe expands, what could it expand into if there is no outside? The grammar of into assumes a container, and cosmology quietly refuses that premise. Return to what general relativity actually claims. Space is not a container that holds matter, like air inside a jar. Space-time is a geometry that defines distance, time, and causal reach, and matter tells that geometry how to curve. In Einstein's view, the stage and the actors are coupled, and the script is the field equations. That historical shift matters because Newton's absolute space made outside feel natural. Relativity replaced that intuition with a relational world, where measurement is part of the structure. So the core answer is simple, and it stays strange even after you accept it. Expansion is not motion into pre-existing space. Expansion is the internal change of distances defined by the metric, the rulebook for how rulers and clocks add up. In the FLW picture, galaxies at rest in co-moving coordinates can still separate as the cosmic grid stretches. Proper distance grows because the scale factor AT grows, and that growth is a property of spacetime itself. The galaxies are not fleeing a center. The definition of between is evolving. This is why the opening image fails. An edge would be a boundary where geometry ends, a place where geodesics stop because there is nowhere left to go. Standard cosmology does not require such a boundary. Whether space is infinite or finite, a finite universe can be unbounded like the surface of a sphere, where you can travel forever and never meet a wall. The balloon analogy helps only if we keep the caveat, because the rubber surface is the universe in the model. The outside in the drawing is not part of the physics, even if the eye keeps looking for it. A flat universe can also be finite, if topology wraps space around in a global identification. A torus-like identification can make paths loop without any wall, so straight lines can return like longitudes on a map. Again, there is no external arena that must receive the expansion, only a changing internal scale. Now we tighten the language around recession, because the word speed is where intuition often breaks. The raisin bread picture is useful for intuition about the Hubble flow, especially when the loaf swells uniformly. Each raisin sees others recede with no central raisin, and the pattern looks the same from any ordinary point. But the most precise view is the metric expansion view, and it is less cinematic but more honest. Recession speed is the time derivative of proper distance, not a local rocket speed measured in one inertial frame. That is why superluminal recession can occur without breaking relativity, because no object locally outruns light through its nearby space. Light still obeys its rule in every small neighborhood, yet the space between neighborhoods can grow while the light is in transit. Visually, imagine a photon crossing a grid whose spacing increases, so the remaining squares keep multiplying ahead of it. The result is redshift, not because the source slows, but because wavelengths track AT as the geometry evolves. So what is the universe expanding into? Into nothing, if nothing means no external space is required and no surrounding void needs to be carved out. The equations evolve the geometry internally, and that is enough to generate increasing distances and stretched light. Now we clarify the word nothing, because it carries hidden assumptions that sound alike but differ physically. Nothing can mean no matter, no particles, or no space-time at all. Physics treats these as different claims, and confusing them makes the paradox feel deeper than it is. First meaning, the universe does not need external space, even if it is finite, because outside is not a coordinate in the model. Asking for an outside is like asking what is north of the North Pole, where the question keeps its grammar but loses its map. Second meaning, empty space in quantum field theory is not nothing, even when it contains no real particles you can count. The vacuum is the lowest energy state of fields, and it still has structure, fluctuations, and measurable consequences. In plain terms, it is quiet, not absent. Those fluctuations are not a cartoon of particles popping in and out like fireflies in darkness. They are correlations required by uncertainty, and they show up in how fields cannot be perfectly still everywhere at once. Inflation used that fact as a mechanism, not as poetry, because stretched quantum ripples can become classical seeds. Third meaning, before time may be undefined in classical terms, and that is not a loophole but a warning label. The Big Bang singularity in GR is geodesic incompleteness, a sign our description breaks when curvature and density blow past the theory's domain. Near the Planck era, time itself may not be a usable parameter, because the very notion of a smooth metric could fail. This is where humility becomes scientific, not rhetorical, because it marks the boundary of tested inference. We can say with confidence what expansion means in our best tested framework, and we can trace it through data. We cannot say with confidence what replaces the earliest boundary of that framework, or whether replacement is even the right metaphor. We can also say what drives AT in the equations we trust, and the driver is not a shove from the edges. The Friedman equations tie expansion to energy density and pressure, including the surprising role of negative pressure in accelerating expansion. Matter dilutes as QR3, radiation as A-4, and vacuum-like energy stays roughly constant as space grows. That bookkeeping resolves another hidden confusion, because it separates cause from appearance. Expansion is not caused by galaxies pushing outward, as if they were fragments in an explosion. Expansion is the geometry responding to the universe's stress energy content, and the matter simply rides along the evolving metric. Now connect early and late acceleration without merging them, because the similarities can mislead. Inflation was a brief early phase that smoothed and seeded the observable universe, leaving a near-uniform background with tiny patterned anisotropies. Dark energy is a late-time acceleration that reshapes horizons and future observability, thinning the cosmic web into isolated islands. Both episodes point to vacuum-like behavior, and that is unsettling if you stare at it long enough. The vacuum seems able to dominate cosmic history at radically different energy scales, as if empty were an active ingredient. We still do not know why, and the ignorance is structural rather than merely technical. The cosmological constant is the simplest fit to late-time data, and simplicity has a long history of being both guide and trap. It behaves like W near -1, with constant energy density and negative pressure that effectively pulls space apart. Yet quantum field theory naively predicts vacuum energies that are absurdly larger, by many orders of magnitude. That mismatch is not a detail, and it is not solved by better telescopes alone, because it lives in the foundations. It is a deep problem in how we connect quantum theory, gravity, and the meaning of energy in curved spacetime. It is why nothing is one of physics' most loaded words, and why the simplest term in the equations can be the most mysterious. We also do not know whether dark energy is truly constant, even if the data currently allow it. It could be a dynamical field that evolves slowly, or a sign gravity changes on large scales where we have fewer direct tests. Current constraints favour W close to -1, but the door is not closed, and the hinge is precision. Bring back the Hubble tension as a live example of uncertainty that is both technical and conceptual. Local distance ladders prefer a higher H0 than CMB inferred fits, and the gap has persisted across improved measurements. The outcome could be hidden systematics, or new early universe physics that changes the sound horizon and ripples forward into today. Either way, the tension reinforces the theme. Cosmology is inference from relics, not a view from outside, and the relics are filtered through models. Our conclusions depend on cross-checks, assumptions, and the limited information the universe allows, because light and causality set hard boundaries on what can be compared. Now return to horizons, because they shape what questions remain meaningful and which ones dissolve. The particle horizon limits what we can see now, defining the radius of our observable past. The event horizon in an accelerating universe limits what we can ever see, even given infinite patience and perfect instruments. This matters for the paradox because it reframes outside again in a more precise way. The universe can be larger than the observable patch, and parts can be forever causally disconnected without any separating wall. Outside is not a place beyond an edge, but a confusion between global reality and local access. So we can finally resolve the opening hook without deflating the mystery, because the mystery was partly a misaimed question. There is no edge to stand on, because space is not a thing inside a room. The room is the geometry, and geometry is what changes, quietly, everywhere, all at once. What remains open is not where the universe expands into. What remains open is why space-time has the properties it has, and why the parameters fall where they do. We do not know the initial conditions, why inflation started if it did, or how it connects to particle physics without fine-tuning. We do not know what happened in the Planck era, where quantum gravity should dominate and classical spacetime may dissolve into something else. We do not know whether time emerges from something deeper, or whether the question of before is simply ill-posed. We do not know why L has its observed value, or why vacuum energy gravitates the way it does. We do not know whether dark energy is a constant, a field, or a modification of gravity, and each option changes the far future. Yet we do know what we mean by expansion in modern cosmology, because we can operationalize it. It is the evolution of the scale factor, the stretching of proper distances, and the redshifting of light as wavelengths track AT. It is a geometric statement, not a frontier advancing into emptiness, and that distinction is the whole resolution. The paradox dissolves when we stop treating space as a container and start treating it as a participant. The universe is not expanding into nothing. It is expanding by changing the very rules that define distance, and by changing what far even means. End on the human limitation that created the paradox, because it is not a flaw so much as an inheritance. Our minds evolve for rooms, edges, and backgrounds that stay put, where motion means crossing a fixed stage. Cosmology asks us to imagine a reality where outside is not a place, but a mistaken question. So when we ask what the universe expands into, we're really asking what we are allowed to picture and what our metaphors demand. Physics answers with geometry and then leaves us with the deeper mystery. Why this geometry? Why these fields? And why does even nothing refuse to be simple? We began with a paradox that feels unavoidable, an expanding universe with nowhere to go, and followed the evidence that forced a quieter answer. From Slipher's redshifts to Leavitt's Cepheids and Hubble's distances, the sky kept repeating the same message in every direction. Space itself is changing. General relativity then flipped the intuition, turning space-time from a passive stage into an actor, where distance is something the metric decides and light faithfully records. The CMB's near-perfect blackbody glow, the acoustic peaks, nucleosynthesis yields, supernova acceleration, and BAO standard rulers all converged on one story, a universe whose scale factor has evolved through radiation, matter, and now a vacuum-like component. Along the way, we learned why there is no center to point at, why recession can exceed light speed without breaking relativity, and why flat does not automatically mean infinite. Inflation offered a compelling prologue, smoothing horizons, diluting curvature, and seeding structure from quantum fluctuations, yet it also deepened the question of what vacuum energy really is. And the late-time acceleration sharpened the limits of what can ever be known, because an event horizon is not a wall in space, it is a boundary in causality. The unresolved threads are not loose ends so much as signposts, pointing toward the script behind AT, the nature of pressure and energy components, the Hubble tension's hint of missing physics, and the Planck-era gap where classical spacetime may not apply. So what is the universe expanding into if there is no outside to spill into and no edge to stand on? In modern cosmology, it expands into no place at all. Expansion is the geometry rewriting what father means, while nothing becomes a question about vacuum, causality, and even the existence of space-time itself. The deepest mystery, then, is not where the universe is going, but why the laws that shape space-time choose this particular history of stretching. If nothing can have structure, fluctuations, and gravity, then the most alien frontier may be this, that emptiness is not the absence of reality, but one of its most active forms. If you want to keep pulling on this thread, follow the next measurements of W, the Hubble tension, and primordial signals, because the next clue may arrive as a faint pattern in ancient light,